Every time you come around, you know I can't say no. Every time the sun goes down, I let you take control. I can feel the paradise before my world goes. And tonight, I saw you before. My bad habits lead to late nights and alone conversations with a stranger I barely know. Swearing this will be the last, but it probably won't. I got nothing left to lose or use or do. My bad habits lead to white eyes stare in space, and I know I lose control of the things that I say. Yeah, I'm just looking for a way out now. I want to escape. Then I was talking to you. It's true. It's true. My bad habits lead to you. My bad habits lead to you. Every pure intention ends when the good times start. There is the first time spark. It's like your lights and I only later nights and then alone conversations with a stranger I barely know. Swearing this will be the last, but it probably won't. I got nothing left to lose or use or do. My bad habits lead to white eyes stare in space, and I know I lose control of the things that I say. Yeah, I'm just looking for a way out now. I might escape. Nothing I can stop to. It's true. It's true. My bad listen to you. Listen to you. Took a long way down. Nothing happens up to. It's true. It's true. My back listening to you. Maybe you can show me how to love. Maybe I'm going through a dose. You don't even have to do too much. You can turn me on with just a touch, baby. I don't know. Been sitting for an empty. I don't want the world to judge me. I can see clearly when you're gone. Or not. So I can see the sunlight up the sky. So I hit the road and overdrive. Baby. Oh, city full and empty. Oh, what around to judge me. I can see clearly when you're on, on my step. Think about the Lord. Same thing. I'm trying to put you in the worst mood. Me one cleaner than your dress shoes. They point to just to hurt you. All that left just to please you. None of these toys only do. Want your whole year in a week too. Main bitch out of your league too. Side bitch out of your league too. I said one thing need a centerpiece. 20 rocks a table come from Ebony. Like I've been to 20 pieces. That chicken up with the face, of my baby. You talking money, need to hear the name. You talking money, I don't give a shit. Switch up my side, I like to get it lit. Switch my car if I kill any pain. Look what you got. Every day a nigga try to test me, yeah. Every day a nigga try to hit me, yeah. Pull up in the road to FBI. It's overweight and guilty, yeah. Coming for the king, that's a fuck right. I'm alive in the fuck time, man. The competition, I don't really listen. I'm in the blue new song, bumping new edition. That's the one thing need a centerpiece. 20 racks a table come from Ebony. Cut that up into skinny pieces. Then she clean up with her face, man, I love my baby. You talking money, need to hear her name. You talking about me, I don't give a shit. Switch up my side, like to give you me. Switch up my car if I kill anything. Look what you did. Let a nigga brag, legend of the fall to the year like a bandit. Bought my mama a crib and a brand new wagon. Now she hit the grocery shop looking lavish. Star Trek roof in the Wraith the Con. Girls get loose when they hear the song. 100 on the dash, give me close to God. We don't pray for love, we just pray for cause. House so empty, need a centerpiece. 20 racks a table come from Ebony. Cut that ivory into skinny pieces. Then she clean up with her face when I love my baby. You talking money, need a hearing aid. You talking about me, I don't see a shade. Switch on my side, like to get it late. Switch on my car if I kill any pain. My baby, oh, you don't love me, you don't love me, you don't love me, but that's okay. 'Cause I love me, I love me, I love me, I love myself anyway. Hey, everything's gonna be alright. Everything's gonna be okay. It's gonna be a good, good life. That's what my therapist said. Everything's gonna be alright. Everything's gonna be just fine. It's gonna be a good, good life. Something I would think on me just to the feeling. You don't love me, you don't love me, you don't love me, you don't love me, but that's okay. Sorry, you love me, you love me, I love myself anyway. Hey, everything's gonna be alright. Everything's gonna be okay. It's gonna be a good, good life. That's what my therapist said. Everything's gonna be alright. Everything's gonna be just fine. Talking in my sleep at night, making
Hello, everyone, and welcome back to the next session of the Gravitational Astrophysics Symposium. We have 4 talks in this session. The first speaker is Stephanie Brown, who will be telling us about whether neutron star tidal effects can mask deviations from general relativity. So if you could put the slides up.
Right. Okay. The mic is working. Hello, everyone. I am Stephanie or Alex Brown, and I'm going to be talking about, as you said, whether neutron star tidal effects can obscure deviations from GR. I'm currently working at the Oscar Klein Center in Stockholm, but a lot of this work was done. Oh, press the button. A lot of this work was done during my PhD at AEI Hanover with that group. And I'm very happy to be sharing this call with you. I pivoted from a poster to a talk a bit at the last minute, so for any mistakes, just blame that. Okay, next, right. So I like to first talk about why we care about this subject, right? Like before I tell you about it, why do we want to do it? Neutron stars and neutron star mergers have impact in a lot of fields. For instance, they're unique laboratories for studying the physics of ultra-dense nuclear matter, specifically cold nuclear matter. They probe a regime of nuclear physics that is outside of our capabilities to probe here on Earth. They are useful for testing general relativity in the strong field limits. Neutron stars and black holes are some of our best tests of strong field gravity, where we expect to see any deviations from GR. They are also very important to the new era of multi-messenger astronomy, and we heard about that earlier during the amazing plenary talks. And of course, they have a bunch of other things, but one that is very interesting is that they are an important source of heavy elements and important to the chemical evolution of our universe. Now, of course, I only have like 12 minutes, so I'm going to focus on these 2 things and how these 2 sort of play off of each other, but there'll be talks later about multi-messenger and about all the other things. So I hope you see those talks as well. So I want to clarify what exactly we can learn from gravitational waves from neutron stars. So we know that we have 2 BNS and a few NSBH mergers, and we got a lovely introduction to that during the plenary talk. And we have learned a lot, but specifically, let me see if I can use the laser, there we go. The things that we very specifically measure from the gravitational wave are the component masses and the component tidal deformabilities. Those are the parameters, or 2 of the parameters that are in the gravitational waves that are of most interest to constraining the nuclear equation of state. Using the nuclear equation of state and a bunch of different methods, you can retrieve the radius and, of course, the equation of state. But these are sort of inferred properties. These are your directly measured properties. And of course, you can test strong field gravity in so many ways that it is its entire own talk, and I don't have time to talk about how you can do that. So I want to clarify a bit about the nuclear equation of state. It is, from a nuclear physics side, a pressure, density, and temperature relation. For neutron stars, we can ignore temperature. It is constrained at low densities by nuclear physics experiments and at high densities by perturbative quantum chromodynamics. But in the middle here, it is very uncertain. And this is the region where neutron stars can help us learn things. And the equations of state that I use for my analysis are defined by what's called chiral effective field theory. They've come from some colleagues who are at Los Alamos and Syracuse University, and they are defined by chiral effective field theory in this region, and then they sort of freely go by speed of sound in this region. Now, in terms of astrophysics, we generally think of the nuclear equation of state more like this, as a mass radius or a mass tidal deformability relationship. And how you get from this nuclear physics relation to an astrophysical relation is by using the structure equation, so the Tolman-Oppenheimer-Volkov equations. Now, the TOV equations are specific to general relativity. If you want to look outside of general relativity, you're going to have different structure equations. If you add a scalar field, if you add a vector field, you're adding things to your structure equations, which means that the same thing here gives you different results in this mass radius space. And you can see that this sort of somewhat narrow-looking uncertainty leads to a very huge uncertainty in the nuclear properties, and that's an important thing for this project. Right. So that's, I hope, enough introduction. I'm going to talk about how we do this. What is the methodology that I'm using here to explore the interplay between the EOS uncertainty and the non-GR? So I'm using Bayesian inference of GW170817. And specifically, I'm using scalar tensor theory as a test case to compare to GR. Scalar tensor theory is perhaps the most straightforward alternative that we have to general relativity. You add a single scalar field. And the reason that we use this one specifically is that the excuse me, the tidal deformability calculations are tractable. When you get into complex and more realistic theories of alternative theories of gravity, these equations that are like perturbative, general relativistic are very complicated and you only have numerical solutions. So we start with sort of simple model in this work. And we sort of take the chiral EFT, so our nuclear physics information, and we combine this with the structure and tidal equations. We do one set of GR, so we have a control. We just analyze 170817 assuming GR. And then we add in analysis for scalar tensor theory. And what we get out, what we get from our chiral EFT and our structure equations are mass radius tidal deformability relations. And this is what we're putting into our analysis. This is what is changing. So we have general relativity, and then we have an alternative theory of gravity, and we're going to compare those two things. So we combine that with our 170817 data, and we get out a posterior or a measurement on the mass radius and the tidal deformability. And then the last thing that we want to do is compare that to the other astrophysical constraints we have. And so we use some E&M data to further sort of slim down our results. And that's sort of the basic outline of how this works. So I have to have a Bayes theorem slide because I'm doing parameter estimation and it's obligatory. So what this tells us is that our posterior, so how likely a given parameter is given our data and a hypothesis, which is a waveform. And this is related to what's called the likelihood and the prior. And the prior is the a priori information you have. So we know that neutron stars are between 1.4 and 3 or 1.4 and 2.5. And we expect, the tidal deformability of a neutron star to be strictly greater than 0. And this prior information is what is changing in our analysis. So the mass radius priors are changing between general relativity and scalar tensor theory because of that change in the TOV equations. And then you have the likelihood, which tells you how likely the data is given a variable and your hypothesis. And like I said, you combine those and you get your posterior, which tells you how likely a given variable is. And we want to compare this for the two different theories. Right, so I have my, what did we find, right? So I have on this side general relativity, and on this side scalar tensor theory. These plots show the exact same thing. So I'll break it down just pointing at one to start with, because there's a lot going on here. So these lines in the background, and I'm not sure you can see, there's some here. These are our equations of state. There are 2,500 of them, and as I said, they are informed by nuclear physics at this sort of low density regime. And the color corresponding here is how supported it is by the data. So the darker the line is here, the more support it has from our analysis. And you can see here that when we go from this mass radius relationship and general relativity to the scalar tensor relationship, your same nuclear physics gives you very different astrophysical properties. Specifically in scalar tensor theory, you get this sort of bend in the equation of state curves. This, like how this changes to this depends on your theory, but the deviations can actually be quite large, as you can see. And so on top of our sort of equation of state, we have our mass radius posteriors. We have sort of the two-dimensional posteriors here, the 50 and 90, and then you have the one-dimensionals on the side. And then on top of that is our E&M information. So we have this dashed line here. This is the heaviest known pulsar so far, which is J0952 minus 607. And this has a minimum mass of about 2.18. And so we required that all of our equations of state meet this minimum mass. So we want our analysis to be consistent with E&M. So we get rid of anything that's not consistent with E&M. And then we also include two NICER pulsars in this analysis. This is the higher mass NICER pulsar, and there are two publications on it. So that's why there's two colors here and same here. This is a separate NICER pulsar with two publications. And I require that any equation of state is consistent with one of these papers, which means that our results are completely consistent with E&M. We're excluded anything that doesn't agree with our electromagnetic observations. And the first thing you can see if you look at these mass posteriors is that the masses are 1.57, 1.21 are pretty much exactly the same in both. And this is not surprising because, as I said, mass is what we are directly measuring from the gravitational wave. What changes is our radius, and this is because we're inferring the radius using the equation of state. And so if you look at this posterior here, you get about 1.24 for both of your objects, the higher mass and the lower mass. And if you've seen previous analyses of 170817, you may think that this is a bit a bit high. A lot of analyses have a sort of closer to 11, but this is because we required this high mass cutoff, and these sort of equations of state in this regime are cut off by this high mass. So that's why these are a bit larger than what you might see in other analyses of 170817 alone. And so you see this are about consistent, but if you look at scalar tensor theory, we have a splitting. You have one at about 13.3 and one at about 12.3. So the first thing that is important to notice is there is a difference between general relativity and scalar tensor theory. There is something going on that is different. However, there's an important response to that, that is, we wouldn't know, like if I didn't tell you that this was scalar tensor theory and it didn't tell you this was general relativity, we wouldn't know which one of these is correct per se, because they're both completely consistent with all of our other measurements. And this is a problem because if you want to say you want to test GR, you want to see if scalar tensor theory is true, and you use a waveform that is scalar tensor theory, but you just assume that you have the general relativistic tidal effects, you're going to get out incorrect information and you're going to get the wrong equation of state. And when you're trying to infer the equation of state and you're trying to test GR simultaneously, you can see that there is biases that will show up if you aren't properly taking into account here the physics of your different theories. Yeah, so that is the main point here, is that right now there is a difference that could be observable, and this difference is sort of being observed in our large uncertainty on the equation of state that we have right now. And it's possible that if we have better E&M observations, we would be able to separate these out. So for instance, if you have only these blue, the Riley analyses of the nicer pulsars, you can see GR is much more equivalent with those. And then if you have the scalar tensor theory, the two red which is the Miller et al. Analyses, are more consistent. So this is something where multi-messenger analysis or just combinations of E&M data and GW data could be very useful for looking at tidal effects outside of GR. That is actually the main takeaway. I might have been talking a bit fast. I think I'm going through my time quite fast. But yeah, that's the main takeaway, is that we need to be careful when we're testing GR with BNS. We can't just assume that general relativistic tidal effects or general relativistic mass radius effects are good enough, especially with future detectors where we get even better measurements here. We need to be careful. Right, so a little bit of where to go from here. This can be combined with the non-GR gravitational waveforms that are just now getting to the point where you can do parameter estimation with them. Of course, it'd be good to look at more realistic and more complex theories, and sort of saying what will we have for future detectors, including our future E&M observations. That's everything that I have. I'm happy to take any questions.
Thank you for the very nice talk. Ryan, is the microphone coming?
Yeah, thanks for the talk. I was wondering, like, the nicer results would also be assuming general
Yes.
relativity. So do you know how their results would be impacted if you change to scalar tensor theory?
Unfortunately, I do not. I don't work directly with NICER. They would definitely change, and if you want to do this like very well, you would need to, do both analyses like jointly, of course. But again, this is sort of a first order look at what's going on. But yes, absolutely. If you wanted to actually test, you would need to do that for every single input stream.
Thanks, yeah, very interesting talk.
So what are the prospects for actually testing GR in this way? Do you need multiple events?
With the tidal
start to
effect?
see, yeah.
I would say definitely yes. I mean, 170817 is currently our best constraint on the tidal effects. the other the NSPH systems are unfortunately not super helpful because they only have one. Although if you combine that with an E&M observation, it can give you a lot more information. So I think it's not just the GW side. We need to combine it with the E&M analyses. So I think it's hard to say because it depends on the telescope and the analyses of the nicer pulsars, and then also on what the universe gives us in terms of neutron stars.
Thank you. Any more questions? In that case, let's thank Alex again.
Thank you.
Okay. Our second talk is from Clecchio. Is that the right pronunciation? Clecchio, sorry. And he's going to be telling us about measuring the Hubble constant using gravitational observations with ground-based detectors.
Hello, everyone, and good morning. My name is, let me just check, that's Clécio Debon. I'm from the Brazilian Center for Physics in the beautiful city of Rio de Janeiro, as you can see here, where we have an AI lab for physics. And I'm going to talk to you today about the last results we have on the Hubble constant using dark standard sirens. Well, as many of you are probably aware, today we live in a cosmological scenario where we have a tension between measurements related to CMB related or early universe measurements with the more recent universe measurements, where we see this tension in the Hubble constant that it's growing and growing as the time goes by, right? So one of the possible solutions would be to have a gravitational wave, an independent probe measurement over the Hubble constant that could arbitrate this tension. So there has been many papers about this subject, and most of us already know that we have the greatest event of JW17 or 817, which we could actually see the electromagnetic counterpart. So it gives us the hint of how this method could be useful. However, since then, we couldn't find, almost 7 years later, we couldn't see any other electromagnetic counterpart yet. We do have, as you've seen in the talk in the plenary morning session this morning, there have been some claims about a different kilonova, like this one and this one, that was very well measured by the JWST. However, we couldn't find a gravitational wave in connection between for multiple reasons. Maybe just because the LIGO was off, or simply because they might not necessarily be neutron star mergers. It might be white dwarfs with neutron star mergers, and so on. So we are not completely sure about those events, but the fact is we only have one bright siren up to the date. So what can we do? Even if LIGO detects the neutron star merger, it's not completely clear that we are able to see. If we have a very bright and blue kilonova like the one in JW17 or 817, this is the discovery probability in this recent paper using DCAN detection strategies for a kilonova, right? So using an optimized strategy, we could see almost to the limits of LIGO can see. However, if we find a more redder kilonova, which I'm not completely sure if the kilonova will be like the one we have in 2017, this probability can drop a lot. And if it's a neutron star merger, as you saw in the plenary, the probabilities are low that it can, a neutron star black hole merger, probabilities are even lower that you can find an electromagnetic counterpart. So we can see at the edge at something around 50%. Well, what can we do in this scenario? We need around 50 kilonova with electromagnetic counterparts well measured to reach something like 2% level Hubble constant, which would be the precision level required to arbitrate the tension. But we can use the dark siren method. The dark siren method It relies on the idea, and you can assume a probability of being host of every galaxy in the field of a gravitational wave event. It is a well understood formalism that's been done since at least 2017. We perform this, we update these constraints right now using the updates from the LIGO maps, and also some events well defined in O4, right? So to do that, we use a blind analysis. We use PhotoZ, photometric redshift of all galaxies in the field. We produce our own PhotoZ. We take in account as many of selection effects as we could using good simulations by BiStar, and we didn't put any luminosity weight, so we don't assume that any galaxy is more likely to be the host of any other in the field. This choice is simply because we are not completely sure about the hosts, as we only have one good, well-measured event, right? So this method has the advantage of being applied of many events. So you don't require to be neutron star merger. You can use most of the BBH measures if you have the right coverage in PhotoZ. So you need the big areas of PhotoZ coverage and well done PhotoZ. And that's what we did, okay? So these are the events we use. We select 15 events that are well covered over the legacy survey in a Delve footprint. These are surveys done using DCAM, so the same instrument that is used by the dark energy survey. So we use all this data that is printed here, and we select 15 events that are below 1,500 megaparsec of distance, so they're not very sensitive to omega matter, for instance, with at least a probability of coverage of over 70% over the footprint. So these are the events we selected. Okay, most of them are from O3, and a few of them are the recent events from O4. Okay. So in order to have a good estimate on the Hubble estimate, you also need good photometric redshifts. And that's where AI comes into the play. The footprint over DCAM is not homogeneous, right? So some areas doesn't have all the bands, some have 3 bands, some have 4 bands. So to deal with that, we use a deep learning method that estimates the full probability density function, okay? So we use this recurrent neural network where we could and add it to a mixture density network, so we can obtain the full probability distributions of all the galaxies in the footprint of DCAM. This is a huge catalog, and is also huge because we contain all the PDFs, not only the point estimates. So we can have some effects like this one. This is a Gaussian approximation if you have a point-like estimation, and this is the full PDF. So you can see here we have multiple peaks. So you gain information over the PhotoZs by doing things like this. Okay, so this is the validation of our photometric redshifts. Okay, so Z-phot and Z-spec over the range of interest of the gravitational waves I mentioned. This is a sum of the consistent tests over the PDF, so we can actually measure if the PDF is reliable enough or not. So this is the PIT and the odds distribution, for instance. For an ideal case, we would see something like a distribution in this line uniform. This means that we have a little bit of bias towards lower redshifts here, but we take this into account in our method. We correct by the PhotoZ bias. This is the point statistics that we have, the sigma and mad, and this is the results from our group. This is point estimates from the legacy survey public, and from a previous paper from our collaborators. Okay, so you see they are consistent in terms of point-like. However, they do we carry the information of the PDF over the whole constraint of H naught. Okay, all right. So here is some of the posteriors we obtain using dark siren methods in 6 of the 15 events. I just select this. So you can see the effect of using the full PDFs, Gaussian approximation, and the legacy public data, the public PhotoZ release. We can see, for instance, there is an important difference between the legacy public. We are very confident of the PhotoZ estimates we did within our methods. And they are mostly consistent with using full PDF and Gaussian approximations. However, we see some effects like this one. So this is the full PDFs and using Gaussian approximations over the PDFs we obtain. Okay, and this is the legacy public. So they don't seem very different in terms of PhotoZ, but once you input in the posteriors, the small advantage that we obtain in the PhotoZs make the difference, right? As you can see in this event. Okay, so this is the combined constraint you obtain. So this is the dark siren only. Okay, this is the GW17 0817 constraint. So we have right now a comparable constraint between the first bright siren, the first and unique bright siren up to date, with the dark siren method that we have. Okay, and a combined constraint with recent jet constraints with very long baseline interferometry. We obtain this. Okay. All right. So where we are on this? We reached the point where the catalog method obtained this kind of constraint, so 18% constraint, a single bright siren. Let me find it here. Oh, here it is. It's 18%. So we reached approximately the same level of precision of a single bright siren, using only 15 events with well-measured photometric redshifts. Okay. If we combine all of them with the recent jet constraints, we could obtain this measurement here, which is a 6% error, sorry, with error of 4 plus minus 4. Okay. We also made a cross-check using a different run over the full catalog. So we get the public PhotoZs from the legacy survey. They were consistent with the results. We also got the same run over the same data with a different pipeline to obtain the catalogs again and run again the PhotoZs and obtain similar constraints. We select the one that where the quality of the PhotoZs were the best. Okay, which are this constraint that you see here. Oops. So we also take into account in terms of selection function. So selection function is dependent over the BBH mass population, which is still, well, it's well constrained during O1 and O3. However, we still have some questions about it, and the selection function does depend over the mass distribution of the BBH. So we did different tests with a simple power law, BBH mass distribution, and also different choices over it, like a power law plus peak, which would be the standard way of doing this today, and also more exotic or different choices of selection function. And we still have a negligible error around 0.7%. So the method is still good, even if we are not completely sure about the BBH mass distribution. But that's not enough. As we increase the number of constraints, we're going to see a lot of selection effects taking not a lot of biases taking place. So we are working on it right now, so we can get more and more reliable constraints. So we are now working on any-body simulation to take into account the effect of galactic incompleteness. We do take this into account as we have a volume limited sample. But we are going to look at this more carefully. We are going to take a look on how we get biases by weighting the galaxies. We didn't weight at this analysis, but we are analyzing this. Raynaud, and the effects of the wrong selection function. We have a preliminary test, but this will be more and more important as we add more events, right? And the impact of the photo Z systematics that, and especially the unknown systematics that we might have, okay? So this is my concluding remarks. So the dark siren methods require high precision photo Zs, okay, in fairly complete catalogs. So that's why it's important to make a cut over the distance, not only because of the effects of omega matter that we are not constraining here, but also because of the completeness of the catalog. Okay, up to now we have these 15 events, and the precision is similar to a single GW170817 event. Okay, which is this one here, around 18 to 20%, depending on the paper. So we have presently, as we heard, the number of bright sirens might be very low. We are reaching around the lower bar, right? Which can be at, as far as I remember, something like 2 or maybe even 0 events. So the dark sirens might be the best choice for the moment, at least because we don't have another choice if you don't find electromagnetic counterparts. Okay, and BB8s outnumber at least 2 orders of magnitude, like 100 per one. So we have a lot of BBH data that could be used if you have the right photometric redshift catalog. Okay, and also as we increase the precision, and you see that we are increasing the precision, the systematics play an important role. So it's now time to take a good care of this for the dark siren methods keeps competitive as the times goes by. Well, thank you very much for your attention, and I'm happy to take any questions.
Hi, thank you very much for your talk. It's very interesting. I have 2 questions, but I can start with just one. You mentioned also in your final slide saying that the binary black hole mergers outnumber the binary neutron star mergers by 2 orders of magnitude, which is true. But my question is about the future. So currently photometric redshifts of these galaxies and probably extend further than the redshifts of the black holes that we detect, which go out to redshift 1-ish. But in the future, when we have 3rd generation detectors, a lot of the increase in numbers comes from detecting black holes that are much further away. At what point will the binary black hole population outdistance the photometric possibilities? And what is the future of the kind of photometric galaxies? What can we expect in the next 10, 20 years? Out of what redshifts can we get a somewhat reasonable sample of galaxy photometric redshifts?
Okay, yeah, you are correct. If we think about in 20 years ago, we are maybe in a LISA era. What we will see is there will be no photometric data deep enough to make this kind of analysis. However, we can still constrain what we can be done. You use spectral siren methods that's to very far away events, right? So spectral sirens, you take into account only the gravitational wave data with no electromagnetic catalog, for instance, where you rely on the astrophysics of gravitational waves. That's one way. Okay. However, what I do expect that by this age, we don't have a lot of controversy in the Hubble constant. So that's my point over here. So I hope that in 20 years I'll be talking about something different, right? I think my wife can't stand over me talking about H naught for 20 years more, right? So that's my expectations.
Thank you. So just one final question. The results we're getting are somewhat more precise than the results being published by the LVK using all of the dark sirens. Can you comment on that?
Okay, so the results by LVK, they do rely on BBH population. So they are fitting the BBH population together. This gave you astrophysical information from the gravitational waves itself. We don't, so that's a point. But the main difference between the analysis of LVK and the analysis I'm presenting to you is the catalog. So this is a catalog method, so the catalog. They use the GLAD catalog. The GLAD catalog is an old sky photometric redshift catalog. They are way shallower than the catalog I'm showing you. So I don't remember perfectly, but it's something like a complete over 40 or 50 megaparsec, as far as I remember. I may be wrong. I have to check myself. However, this is a fairly incomplete catalog and shallow catalog than the one I'm presenting on. So that's likely the main reason the LVK results are less precise than the ones. So we did a selection over the best informative events. The LIGO used the whole O3 catalog, which is something like 43 events. And you see that many of those events are very, very low information over the H0, since we don't have a deep enough catalog. And most of the constraints are related to the astrophysical BBH population fits they're doing. So the actual source of information is different from the information I'm presenting, even though they use catalogs.
Okay, thank you. Let's thank Felicio again. Yeah, the next talk is also on measuring the Hubble constant, but this time in conjunction with population parameters. The speaker is Tathagata Ghosh.
Hi everyone, I am Tathagata from IAU GA, and thanks to being present here. So my talk is on this particular paper, which is mentioned in the here. And though from the title, you can see that it's basically the combination of population as well as the cosmological parameter and equation of states. However, from the time constant, I will mainly focus on the cosmology part of this paper. So though in the previous talk, you heard some of the how the cosmological parameters are estimated from the GW sirens, but some of the parts that I would like to highlight here. So there are a couple of kind of sources. One is dark sirens, for which the electromagnetic counterpart are not detected, like all the binary black holes and maybe some of the mergers involve neutron stars, because we don't have the EM detections. And for this kind of dark sirens, currently the LIGO, Virgo, Kagura have two pipelines, that is Icaro GW 2.0 and GW Cosmo Plus. In both these pipelines, what happened? The galaxy catalog are used along with the CBC population parameters are marginalized. And if even both the catalog and CBC population are used, the H0 constant primarily comes from what the mass spectrum or the mass distribution were assumed in the binary black holes. Okay, so even if you don't use the galaxy catalog, which is called spectral serial method, which is completely based on the CBC population, you can see the H0 constant is not significantly different. And the other kind of source, which is called bright siren, like GW 17 or 17 is the golden event, for which we have the M counterpart as well as the GW data. And here you can get the Hubble constant from that. However, so far we have only one event, and we don't know that how much the detection rate of the EM data, EM GW joint observation. So we can use the dark siren method for the BNS event though, but another limitation is the number of VNS merger detection. It's very low. Even if we consider we don't have the M counterpart, the number of VNS mergers are very low. So the spectral serial method primarily depends on how much events you are assuming, because it fits the observed frame mass with the source mass spectrum. I will come into the detail in the further. But what I wanted to stress on this, that there's another information from the neutron star we have, that is tidal deformability, because of the presence of matter. And this tidal deformability primarily depends on the source frame mass. And GW can directly measure those quantities. So we can add this extra information within the spectral serial method to further constrain the Hubble constant, which is improve the uncertainty in the H0 significantly. So let's talk briefly about the spectral sidle method. So GW observed the detector frame mass, that is source frame mass times 1 plus z, which is here. And this is suppose the source frame mass, and you can see the detector frame mass is quite different. Okay, so what the spectral sidle method does, it assumes some parametric form of mass model, and with the GW data that gives the redshifted mass. If you the distance, limits the distance from the GW data. So if you assume some H naught, you can have the redshift, and that redshift can be used in conjunction with the redshifted mass from the GW data, and you can compare both the model, because for different values of H naught, this M1, M2 distribution that comes from the GW will be changed, and you can fit the H naught. So this is the basic structure of the spectral sidle method. So, and moreover, in the neutron star, we have tidal deformation. This tidal deformation have impact on the phase of the GW waveform, and this are generally denoted by λ1 and λ2. And this information depends on the source frame mass of the neutron star, and this is not the independent parameter λ1, λ2. They are connected by the neutron star equation of state. So for the given neutron star equation of state, m lambda is deterministic. So the knowledge of equation of state can gives you the estimate of source frame mass again from the λ1, λ2, because they are related quantity. And in conjunction with the redshifted mass information from the GW data, you can estimate the Hubble constant. This is basically called the mass breaking the mass redshift degeneracy. So this is a typical sample, or the few samples of lower dimension sample space, because I exclude other parameters just for the convenience. So you can see that they are the redshifted masses of a typical neutron star. Okay, and these are the corresponding λ1, λ2, and the distance information. And here we assumed all the priors are uniform, at least for the first 4 parameters. For DL, we use some other prior just for the computational convenience. That's different story. But M1 and lambda, for the M1 and λ1, we don't use any informative prior, or say uniform prior over a wide range. Okay, and suppose we assume some true H naught we know for 70 kilometer per second per mega per sec, and we use the M1, M2, λ1, λ2 information, and we converted the luminosity distance information to the redshift and estimate the source frame masses for here. And you can see here, again, we show the source λ1, λ2, the M1 λ1 and M2 λ2 posteriors, and where no deterministic relation are used that come from the equation of state. What I mean that, so for a given equation of state, you can see m lambda related like this, but this kind of information is not assumed during the parameter estimation. Okay, so when we are doing the spectral sidle method, if we incorporated that kind of information too, it will significantly improve the estimation of the Hubble constant, even for a very few BNS like 5 that we have tested. Okay. So this is the basic structure of the Bayesian formalism. The spectral sidle method, just I want to highlight, use the mass model, redshift model, and cosmology. Okay, so it basically use the 3 source parameters, M1, M2, and redshift, and construct a marginalized likelihood from these 3 parameters. However, when we consider when we try to incorporate that m lambda constraint, we have to incorporate the US model too along with this to further putting the condition that comes from the equation of state. So we have to use another sets of parameters that is related to the equation of states, and we assume some parametric equation of states. As I mentioned earlier, I'm not going to the detail of that part, but yeah, you can check the paper if you want. So to incorporate the equation of state model in the Bayesian framework, we have to also incorporate the λ1, λ2. Okay. So what is the goal of the study? So we have tested that whether the incorporation of m lambda constant into the spectral sidle method is really affect significantly to estimate the Hubble constant or not. And to check that, we have assumed 2 different mass models that are observationally motivated. One is Gaussian and one is double Gaussian mass distribution. And since we consider the current generation GW detectors, and 2 of our LIGO detectors, and 1 is Virgo detector operating at their design 05 sensitivity, that is A+. And so the redshift distribution or the horizon redshift of those GW events are not very large. That horizon distance is around 350 megaparsec in my case, okay, in that setup of the simulation. And we assume that the flat lambda cosmology is the true with h naught equals to 70 kilometer per second megaparsec with omega m 0.3. And we use some particular parametric form of equation of states, which contains some of the nuclear parameters as well as some three agnostic parameters, that is piecewise polytrope here. And yeah, that's it. And since one thing, since all the GW events are restricted to a small volume, we do not check how the redshift evolution model plays the role in constraining the H naught. Here, the redshift evolution model we consider as a power law 1 plus z to the power gamma with gamma equals to 0. Basically, there is a uniform in source frame time. So with the setup, we have considered two sets of events. One is 50 and another subset, which is 5 from that 50 events. Just to check, the 50 events will give you the check that the statistical robustness, whereas 5 is a very conservative estimate of the whether we can estimate the Hubble constant, better including the m lambda constant on top of the spectral sidle method. So from that, I will directly go to the result part. So this is the results from the 50 events following Gaussian distribution. These are the injected parameters shown here. And also the solid vertical and the horizontal lines also shows the similar. So, okay. So when I mentioned here US plus population, that means that we ensure the m lambda constraint with the spectral sidle method, whereas the population levels is leveling for indicating the spectral sidle method. Okay. So you can see some of the parameters are not very significantly different, like sigma 1 or gamma 1. And omega m is, of course, not well constrained because it depends that if the events are very high, that omega m is sensitive to calculate the luminosity distance. In this case, it's not a very important parameter. But you can check these two particular parameters. One is h naught and another is m max. So Hubble constant is significantly constrained. It's not only well constrained, compared to the other method, and it also give a very precise result compared to the spectral sidle method, even for the 50 events, which are distributed within around 350 megaparsec. Okay, and Mmax is almost not constrained for the spectral sidle method. Why it is, I will come to later. But Mmax, if we consider the equation of state, it's well measured because for a given equation of state, you can estimate the Mmax. So since the equation of state is simultaneously constrained with the population and cosmology, Mmax is also well constrained. So from the 50 events, we see that, yeah, the results are pretty good. So can we estimate a good estimation from the 5 BNS events using the m lambda constraint? And the answer is yes. You can see, though the H naught estimation error bar is pretty large, but you can compare with the population only with the spectral sidle method, where it's something very different because of the number of events are so small that it can't fit the mass spectrum with the observed mass spectrum with our mass model. And all the results are expected like the 50 events. You can see that there's a very similarity. But yeah, for the H naught, it's very well constrained. So all the results are from the Gaussian mass distribution, where now I will go to the double Gaussian mass distribution with the same sets, same type of events, like the 50 events, and all the parameters are remain same except the mass distribution. And double Gaussian means the summation of the two Gaussian components with some relative weight. And these are the injected parameters are used for create the GW catalog. And you can see the similar feature, what is observed for mu and sigma here. Similar feature is observed of mu1 and sigma1, as well as mu2 and sigma2. Since the weight factor for the first primary Gaussian is high, so mu1 has some impact on that. But there are very few events near the mu2. So even after putting the m lambda constant, it's not significantly improved, even though the m lambda constants are used. And if we focus on the H naught, it's very, very improved in compared to the spectral sidle method. For the 50 events using this double Gaussian distribution, of course, H naught is also estimated, but the uncertainty is at least an order of improvement you can see from the H naught estimation, as well there's an improvement in the Mmax. So like the other cases, here you also check the 5 events set, and you can again see for the H naught is almost Pratt dominated, which is considered as an uniform, of course, but the uncertainty is again improved quite significantly, as well as the max. And again, the other parameters like mu1, sigma are not impacted because of the very small number of events. If the events is large, then you can see some of the parameters is improved. Now, from this, what is the key insight? From the cosmological aspect, the key, this is the, you can see that the two sets, 5 and 50 events, and I am showing the uncertainty of the H0 and M max. You can see this is the first is the only the Gaussian when the population is used, and the second one is the population plus equation of state are used. So the uncertainty as well as the uncertainty is improved as well as the precision. Okay, when the for the double Gaussian, the improvement is better. Why it is, I come to shortly here. And when the 50 events are used, the uncertainty, it's visible that the uncertainty is improved significantly. Similarly, as I mentioned earlier, that since the equation of states are constrained simultaneously, Mmax has also an impact for both the 5 events as well as the 50 events. An interesting point is here. So this is the injected distribution of the Gaussian and double Gaussian. For Gaussian, you can see that for the given equation of states that we inject here, the maximum mass was though the maximum mass is 2.25 solar mass, the injection due to the population parameters from the observation, it was around 1.5. Okay, so you can even that case we can estimate the Mmax pretty well, even though there is no presence of that relatively higher mass neutron stars here. But for the double Gaussian distribution, we have the higher mass neutron star, at least few of them. And so the Mmax is also better constant, which is also impact in the H0 estimation. For the presence of some higher mass neutron star in the double Gaussian distribution, we can see that the H0 is slightly well constrained as well as the Mmax for the double Gaussian mass distribution. However, incorporating the M lambda constraint in the spectral saddle method gives you a significant improvement here in constraining the Hubble constant. So this is the main key insight or takeaway from this work. And there are some implications that I listed here, and I'm stopped here for now. Thank you.
Thank you. Any questions?
Thank you for the talk. Can you comment on the implication for the next generation gravitational wave detectors? I think you might be able to measure the other cosmological parameters like dark energy or.
Right. So, okay, so for the next generation detector, one advantage is we don't, so if we apply the galaxy catalog method, we can't go beyond certain redshift. So this method does not rely on that. So one advantage is that. And since you have the BNS event from the higher redshift, you can infer the other cosmological parameters. And if by that time the H0 is well constrained, you can use that prior, which will also may help in inferring the US parameters too. So,
do you have some idea that how good the, for example, W of the dark energy parameter?
There was a paper, but yeah, I actually forgot.
Okay, thank you.
Thank you for the talk. Up here on your left. You showed that with the 50 event calculation, you can go down to say a 10% position in H0. What would be needed to go to say the 1% level? Is it simply the number of events, or is there some other floor that is determined by our lack of knowledge on one of the other parameters?
Just a minute, for 1% precision, what?
How would you get to 1% precision? Is it simply the number of events that you need to have,
okay.
or is there some other uncertainty in the modeling that gives you a floor?
Okay, I got it. Yeah, so for the 1% precision, one thing, if you have the EM data, that will bit down your error bus significantly, or the other equation of or the better inferred equation of state also impact on constraining the H0 further. But these are the two things that comes come either from the neutron star equation of state or the EM data, which gives you a very precise measurement of the redshift for a particular event. These are the two things that can improve the H0 uncertainty, I think. Yeah.
Okay, and how about the systematic errors of our knowledge of the distribution of masses, mass model for the neutron stars? That will also be a limiting factor, right?
Yes, of course, that is also a limiting factor, but for neutron star, we have at least some other observations like X-ray or radio, which can give you some idea of the mass distribution, of course. But yeah, if the number of events is pretty high, so one can use different mass model and check what is the best factor to get the preferred mass model. And very idealistic case, if you have very, very large number of events, you can use the non-parametric mass model, but that requires to implement that, you need a very large number of events, which is not possible right now. But yeah, you can at least check several mass models with the current scenario to find which is the best favored model with the current observation, apart from GW.
Okay, thank you. We should move on, but let's thank Tagabata again. Okay, the final talk today is on a different topic, on resonances for black holes, and the speaker is Chandru Brink.
Thank you very much for the opportunity to speak at this conference. I'm John Brink. I'm from the University of the Free State in the middle center of mass of our country. So it's lovely to have you all here. So I'm going to be talking about resonances or applications of resonances around black holes. This is based on work that I did with Marissa Geyer a while back and basically left for a while. And then when the Event Horizon Telescope results started coming out and I recognized some of the estimates for the spin, revisited again with two new students, Corlay and Judith. They both have posters, so some of the details of this talk can be found on those posters. And we'll be taking a deep dive right into the galactic center. So what you see at the bottom plot over here is an embedding diagram on which the locations of resonance effects from Marissa's calculation are actually visible. Just to give you an idea what a resonant effect is, we see they're ubiquitous in nature. We see them in Saturn's rings. They sculpted the locations of our planets in the solar system. And if you see if you just look at the Cassini probe over here, to give you an idea of what effects we're looking at, is that the nature, those rings correspond to resonances with the internal structure of Saturn, as well as resonances with the planets. The very pronounced ones come from resonances with the planets. One thing to think about with these structures is typically a resonance traps light particles over densities form, and then further they can coalesce into having larger bits of matter. In black holes, resonances that we'll be talking about result from orbital resonances. If you look at the geodesics in the Kerr space-time, typically in addition to your rotational, the Kepler frequency, you have two additional frequencies that are libration type frequencies. One, the orbit tends to oscillate between a maximum and a minimum inclination, the omega theta, and the second one, the orbit tends to oscillate between omega r, sort of between a maximum and radius, which I've denoted by basically parameterized with p over 1 plus e and p over 1 minus e, an eccentricity type parameter. It is not the eccentricity. Okay, so when I speak about the resonance condition, it's basically the point at which all these resonances, basically you choose 3 integers and you have a linear combination of these frequencies, which then add up to 0. And what we have, I'll often talk or also be mentioning, is I'll talk about the order of the resonance, which is just the magnitude of the integers that I use to label the resonance itself. Okay, so what we do, these resonances are a subset of all the possible orbits that around the black hole, and it represents a 2-dimensional surface in a 3-dimensional parameter space. And we found a very elegant way of characterizing it simply because of the parameters we chose. And the reason why these things are important, initially the work comes from Emery-M spirals, and then just as an afterthought, I applied it to SAG-A and made a remarkably accurate prediction just on a very simple calculation. So the reason why we care about these things is that we have a theorem in mathematics that whenever you perturb the black hole, you are likely to see the biggest impact of your perturbation at these resonances in certain circumstances. And so, which is the reason why, in fact, they are seen in Saturn's rings and have influenced the way we look at planetary orbits or where the planets are located. Okay, so what we did is we simply characterized all of them, and I need to give you these results because they are useful later on. So typically, what is shown here are those three-dimensional surfaces, basically the locations in which the resonances occur. We've characterized them for all eccentricities and inclinations angles. The important characteristics are that for a fixed spin, they have a very weak dependence on the eccentricity. And they decrease, or they sort of split into a pro and retrograde branch on the equatorial plane. And then typically a resonance surface has its arch-shaped, where your polar orbits are up here. So mathematically, we have complete control of these resonances, which is no mean feat. The other important thing, and the most important part for this talk, is they have a very strong spin dependence. Okay, so typically for Schwarzschild, the resonances are degenerate at a particular semilattice rectum, P star, but then as you switch on the spin, they tend to split into pro and retrograde branches, and simply that splitting increases as you increase the spin. Okay. And what was amazing with the way we approached the problem mathematically is we could get to the point where we actually have analytic estimates of all these results that we can write down with pen and paper, program very rapidly. So that makes for very rapid predictions of where we're going to find these features. And the one formula that you'll see a lot, we see P star, and it's simply this combination of the constants we've used to label the resonance, and that directly gives you the location. So this is a very important formula if you ever want to play with the resonances. But as I say, these surfaces are basically all analytic simple in the sense that they are algebraic and you can evaluate them easily. Okay, so what happened was I'll go through the reason for the prediction we made. And we predicted a spin of 0.5, and I'll go through that argument. And then I wanted to revisit the problem to see if there was actually more to what we'd done, or whether it was just sheer coincidence that we had gotten the spin that predicted, that agreed precisely with the event horizon collaborations, synthesized image that fitted it the best. And so what I'm going to do now is I'm going to make just a Schwarzschild images of where these resonances occur. So this is my nice little analytic picture. And this is sort of to do with Collet's work too. So, sorry, let me just see. Here are all the periods that we have, as well as a rough estimate of the locations and the units for Sagittarius A star. I've managed to restrain my theorist's liberty to actually a real object. And here are the typical periods, and you'll notice all of them are on the dynamical timescale that makes event horizon imaging so difficult. And what I'm going to, okay, so let's just plot them. So here's your primary image. If you look at the thing, you have your Orion disk, and the back is lensed up. Here's the secondary image, so you're seeing the bottom of the disk. And so I'm now, and here initially for Lisa was the resonance we were most interested in, and still is, because it's the most likely to have an overlap with gravitational wave perturbation. So it's the most likely to be seen. Okay, so I'm just going to plot the others just because I wanted to, as my student calls it, a UFO plot. We wanted to make our own UFO plot. So here is where in the image certain timescales take place, as well as their sort of their size. And so we can automatically build up our structure or toy model of Sagittarius A star from the different analytic resonances that we see. So this is Schwarzschild. We're still struggling a little bit with curves, several cases. But what our model was basically that we argued that the resonance would trap particles in a disk. So it would have a visible imprint on any accretion disk. They would slowly migrate. The one thing I should say, resonance effects are very difficult to simulate in a computer. The timescales involved for these structures to form is much longer than you generally can keep a hydrodynamic code stable to actually see their formation. So we sort of, here are the various resonances. So the model we had was fine. We get matter trapped in a resonance, it gets stuck there, and this is one of the properties that the KM theorem predicts. It aggregates and maybe becomes a heavier particle. Then at some point, the resonance can no longer hold it. It releases it, and then it crashes into whatever matter is caught on the next structure, giving out emission. And the emission will then have it be modulated with the orbital frequency of that hotspot in that ring. Okay. And so on the basis of that, you can therefore associate the periodicity you observe as well as any features you observe with a particular resonance. And then what we did is we took into account the fact that this picture distorts systematically with spin, okay? And we can calculate the entire distortion as well as, hopefully soon, the image of it. So the way it distorts is basically then characterized by the bottom V's of those plots I showed you at the beginning, for which we have analytic results. So this is still from some of Marissa's work. What you basically have is that the whole image, you can have the image you were shown were given for the resonances over here, but this whole structure distorts and is only parameterized by one number, namely the spin, and we've got some nice estimates for it. And so we used these spin estimates to actually estimate some from very early observations, VLBI observations. We saw features at that radius. We then went ahead and postulated that the origin of the structure was 2/3 resonance. And then we worked out the structure and we came to the conclusion that the spin would be 0.5. And then when the event horizon telescopes came along, it was the same, and which was the reason for actually exploring these things again to see if it was just sheer luck or and actually to try and put error bars on it. The advantage of this approach is this is a multiply redundant structure. All these branches or possibly resonant structures move in the same way, and so it has the chance of actually having a consistency check if we start seeing other features. So if we can see additional resonant structures or additional features in the image, or in fact in the periodicity around Sag A, we will be able to get the spin. It's a multiply redundant check. Okay, so the only problem with this calculation is I hadn't included the rotational resonance. And so because it was too hard at the time, subsequently things have been, I've got a whole bunch of analytic results that I wanted to do adiabatic inspirals with, and it fell out. So if we now include all the frequencies, and I was a little bit worried that this would actually invalidate the result, but it doesn't. If we record all the frequencies in our resonances, we see that the initial principal scale splits. There's a Zeeman-like a splitting in these resonances that take place, and we now have a complete list of them. So I'm hoping to see structures at these at these length scales and the associated time scales, whose scaling I fully understand, by examining a lot of the results that are being made available from Meerkat about Sag A's frequency and time scales, and actually to look at the observational imprint, which will be the subject of the next the next talk, hopefully. Please, the details of these splittings is characterized in Judith's poster, so please make a turn there later today. And so in conclusion, we have full analytic control of the resonant surfaces, their scalings. I should add this, the actual realization of a particular resonance is dependent on the perturbation you're applying to it. So, but all that I've done is characterize as the places where they are most likely to occur. Okay, so basically resonant surfaces have basically very precise spin-dependent effects that we can go and look for in SAGE-A data. The gravitational wave emission causes quasi-stationary structures that you can have this colliding effect that will result in repeated outbursts where the variability is modulated on the timescales we've characterized, as well as an observational imprint on the disk. And there's a very close correlation between these two. And the sort of take home is that the dynamical timescales that make current Sagittarius A star imaging so challenging may in fact contain a wealth of information about probing the spin and possible departures from Kerr, and give us a way of redundantly testing whether those whether it is in fact Kerr and consistent with GR. Thank you very much.
Thank you.
Thanks for a very interesting talk. You've mentioned that the resonances have a very sensitive dependence on spin.
Yes.
What would happen if you tried to extremalize the black hole? What happened to the resonances?
Well, you're only going to go to maximum spin. And the results actually go up to maximum spin. If you look at the V's on my plot, the top of the V's is where you see the most extreme splitting. And so that is maximal spin. So we'll be able to look at that. But I mean, SAGE-A is not maximally spinning. So for this particular application, it's not interesting.
Yeah, thank you very much. I'm not sure if I got all the mathematical details, but maybe just a connection to more, let's say, discrete distribution of bodies, like you mentioned Saturn rings, or there are these Kirkwood gaps, I think, in the asteroid belt. Would you expect something similar in this S cluster, the fast-moving S-stars, that could these resonances be related to the stability of S-star orbits, or this is not really so much connected?
So the S-star orbits are a lot further out. So this is actually looking right into the center.
But if we have star like very close, let's say, could this be affect the orbits? Like if we go to 100 RG or 50 RG, let's say.
So if you're close, but that's really close in, it's more likely to affect an accretion disk, because the moment you get heavier, then gravitational radiation reaction kicks in a stronger way. And then there's an so our mechanism has an interaction between the strength of the resonance to retain something on that orbit and gravitational radiation reaction to move it out of the resonance. And so that's why I said where Saturn's rings are stationary, and even though not infinitely stationary, they are moving out, where the resonance here in the gravitational waves is likely to collect particles and then release them so that they crash into the next one. So it makes, but that is further out than the S-stars definitely. I don't know. All I've done is characterized where to look that it'll be interesting, and the exact nature of the perturbation or the disk actually is going to determine which of those resonances are realized. But no, so the resonance, the low order resonances, which generally the KAM theorem predicts become the most important, are found much closer in than the SRs currently are. Okay, it's more in the avenue of the Event Horizon Telescope.
Hi, thank you. I was curious, do you know how the presence of magnetic fields affect the location of the resonances?
No, but I do know how to try and start the calculation. So, I mean, literally any perturbation, the 0th order departure from Kerr is going to, what the KAM theorem basically predicts is that and the reason maybe I should have said that, the reason it predicts is that resonances permit a very rapid transfer of energy between systems. That's why they become dominant, or our solar system planets collect there, and the rings of Saturn are formed. So the magnetic fields, you could actually go and you could calculate the impact of magnetic fields on resonances and what the overlap integral is. I mean, even if you go and look at the Reisner-Nordstrom geometry, you should be able to even start the calculation there and learn something. But no, I don't know. But I know if it has an impact, it'll start being seen there. In fact, if you look at many, and I mean, this is a dangerous comment. If you look at a lot of the numerical relativity simulations of SAG-A, you see, and this one of the students pointed out, you see these imprinted line structures on them. And I'm very tempted, which is the reason we're making the image, to actually go and look at those and see whether you don't even see their effect in the full hydrodynamic simulations. That's another thing that I actually want to go and try. So no, I haven't calculated, but you can, and I do know where to start.
Thank you.
So my impression from looking at the EHT papers was that although 0.5 maybe was preferred for the spin, it was also equally consistent with 0 or 1.
Sorry?
So the spin measurement, you said it seems to be 0.5, but I thought from the EHT papers, it was equally consistent with being 1 or 0. So how much do you trust a half? Or is it just because it's in the middle of the prior?
No. Well, I like a half. I mean, I mean, this is what got me hooked on checking again. And so I didn't put any error estimates on my spin determination, and neither did they. And that's actually the reason for looking for these structures, is because if you start seeing more than one ring, I'm in business, and I can actually put error estimates in, and I can look at the timescales, and somehow, I mean, I've been hanging around with the pulsar people looking at timescales. They're much better at putting error estimates on their stuff than the imaging guys. And it's basically trying to combine the information of the location and the time frequency, which I think is the powerful tool. And it's going to be dependent on how carefully you can actually resolve those frequencies over several observations that I haven't looked at yet. So yes, the aim is to try and put error estimates in, but firstly to check the hypothesis that we can actually do it using this. So yeah.
Okay, thank you. Let's thank Jandra again. So that's the end of this session. It's lunchtime now, and we're back here at 1:30.
the spectral features we found in the kilonova, that they, have this P Cygni-like shape. There is the kind of broad similarity between different features.
Hi, Albert.
Hello.
Hi, Albert. I'm Kenta.
Hi,
I'm
Kenta.
Hi, hi. Let me trying. So we are trying to show you in the screen.
Yes.
Yes, now we can see you.
Great. You want me to share my screen and play the video from here, or are you going to do it locally?
Let me see.
Okay, cool. Thank you.
Hey? Yes, I think you can play.
Okay, great.
So the Albert can share the screen and then he can play. Okay. Okay.
Great. And I'm ready when you are.
Okay.
Just let me know when I should start the video.
Yeah, let's wait for a few minutes. People are now having lunch.
Yeah, that's very fair. That's very fair. I'm very sorry I can't be there in person. It looks very
No
exciting.
problem. Yeah.
Yeah. It's good.
All right. I think still many people are missing for lunch.
Okay.
And also two speakers haven't shown up somehow. So let's wait for a few more minutes and we will start.
That sounds great. That sounds great. Thank you, Kenta.
Yeah. So welcome back to the afternoon session. So before I begin the session, is there James Gillanders here? I don't think so. I haven't seen him. And Ian Roder here? Dongwen Tak here? Yes. And Lucas is there? Okay. So there are two missing speakers, so maybe we change some program that you might be the second speaker. Okay, so let's get started. The first speaker of the afternoon session is Albert Sneppen. He will tell us about kilonova evolution. Yes, please, Albert.
Hello, everybody. My name is Albert Sneppen. I'm a PhD student as part of the Heavy Metal Consortium, and today I want to tell you about the rapid emergence of spectral features in a kilonova. Now, this project has been born out of a desire to kind of unify and provide a comprehensive perspective on the evolution of the kilonova in time, to kind of take the different spectra, taken different telescopes across the world, put them next to each other, and describe the emergence of structures and the evolution of structure. So from the first spectrum taken 11.75 hours post-merger, and tracing it from South America to Australia to South Africa, back to South America again, the different telescopes across the world, HST, and taking all of these data sets, putting them next to each other so we can talk about the evolution of the kilonova on an hour-by-hour timescale. And the focus here is really to say, I mean, there's a lot of stories. There's the story of the spectral features we found in the kilonova, that they, you know, have this P Cygni-like shape. There is the kind of broad similarity between different features probing from the optical into the near-infrared. There is the complexity of features in the near-infrared, the emergence at later times of structures. What I really want to focus on in this talk, though, is I think the beauty there is in the very early emergence of structure in the kilonova. So the first appearance of structures. And so to appreciate this, right, we're talking about an object that's very rapidly evolving in time. From the first spectrum taken of the kilonova, which is more than 10,000 Kelvin hot, to just one day later where it's cooled to half of that. This is a very rapidly evolving system. And of course, part of the thing is if you very rapidly cool something in time, that's going to drastically upset the ionization balance of the ejector. Now, changing the ionization balance of the ejector implies, of course, that those elements that are in ionization states, which produce spectral features, will rapidly be formed or rapidly be left, and so those spectral features will rapidly merge and change in time. And this is where we get to kind of the elements we see, the specific spectral features we see in the kilonova. And so I think it's worth just pointing out that when I'm saying this blackbody spectrum, it should be taken with the kind of oddity that statement is. So a blackbody spectrum provides an empirically very good fit to the spectral continuum of the data. I can fit from the ultraviolet into the near infrared from about 390 nanometers to about 2.2 microns, and a blackbody fit is an extraordinary good fit to the data. If I fit the ultraviolet and I extend that fit into the near infrared, I do a very good job of capturing where the flux is residing at each wavelength. Which is a remarkable degree of precision. If I fit each arm separately, you know, the answer is rather coherent between the different arms. And we can't reproduce this from first principles in models. And I think there's something rather deep hiding here. But I wanted to emphasize for this talk, this does not necessarily mean that this object is a single temperature when we observe it. Indeed, we already know examples of this, which is kind of a counterexample, right? So when we see the CMB, we observe something that's remarkably coherent to 1 in 10,000, but that's not what the recombination of hydrogen in the early universe looked like, right? Because hydrogen can recombine at many different temperatures, at 3,000 Kelvin, at 3,500 Kelvin. So what we get is a single blackbody temperature, but that's because different things cancel out. And it's the same thing here, as it turns out. So actually, the expansion and the Doppler corrections tend to cancel these rapid, long time delays across the system, producing an emergence of this blackbody spectrum. Okay, so that's one thing we have to keep in mind. Moving forward, there are modulations on this spectrum. There is a feature here, right? And this feature was the first feature identified. It's tentatively linked to strontium-2. Derek Watson made the first identification in 2019 in his Nature paper with his collaborators, and a bunch of other people, Tomoto et al., Gilanes et al., Vieira et al., Shingles et al., Pognet et al., all kind of made generalizations, testing different parts of this assumptions, and they got a similar kind of robustness of this identification. And what's really remarkable here for us is the nature of these lines, right? Because what we're seeing is a p-Cygni shape, so something that's both absorbing and emitting, absorbing blue shifted and emitting red shifted. And it's a classical thing in supernovae or winds, right? That you see these expanding outflows, light traveling through them, scattering off, light traveling towards you, scattering away, producing absorption, blue shifted, light not moving towards you, scattering into your line of sight, producing rest wavelength emission. And so when we're polar observing a kilonova, the fact that we're seeing this p-Cygni shape means we're both seeing the elements in the polar regions of the ejector, but also probing the elements in the equatorial regions of the ejector. And what's just different in the kilonova context than previous p-Cygni line shapes is really the velocity of the system we're talking about here. Here we're seeing, very broad lines extending, almost a factor of 2 in wavelength. And what that means is we're watching ejecta expanding at 30 or perhaps even 40% the speed of light, right? So it's a very broad feature. But now that's actually interesting, right? Because we have something that's very rapidly expanding and we have something that's evolving very rapidly in time, right? So when I'm saying something is evolving very rapidly in time, I mean it's evolving on a timescale of hours. A supernova evolving on a timescale of months. This is changing on a timescale of hours. And I'm saying this thing is expanding very fast, which means it has very long time delays across the different parts of the thing we're probing. So for instance, the part of the ejector that's been moving towards you at 30 or 40% the speed of light for a day, that's much closer to you physically than the part of the ejector that's just been expanding orthogonal to your line of sight. Now that means that there is a great light travel time delay across the system. And that of course means if you have a thing that's evolving on a timescale of hours, then a time delay on a timescale of 10 hours is a very dramatic thing. So let's do this in a specific example. Let's look at the rapid change of ionization in a kilonova, right? It's cooling rapidly, so the ion state should change rapidly. We have some balance of strontium-3 to strontium-2, which in LTE would be described by the Saha ionization equation, which has this e to the minus ionization energy over kBt. Ionization energy in this case would be around 11 electron volts. kBt at the transition here is around 0.4 electron volts. So this is e to the minus 28. And what you can appreciate here is a subtle change in temperature, just a 5 or 10% change in temperature is a dramatic change in the ion balance of the ejector. And this means that if I'm plotting, the temperatures of the different spectra we see when we're fitting black bodies, then we're seeing something rapidly cooling in time, and a subtle change in temperature would imply a drastic change in ionization. Now, you can do this for a bunch of different electron densities, and touch on that later, but the point is just we should really be seeing the formation of these features as the system cools down. So from the first spectrum taken, or the second spectrum taken in Australia here, 0.92 days, if we just go 6 hours later, by the time the object was over South Africa, we should start to see the thing form in absorption, because that part of the ejector will now have undergone recombination, and so forth as we go forward in time. And so this actually means there's a specific prediction for how lines will emerge in kilonova. And I'm going to show you the result, and then I'm going to try to explain it. So at 0.8, 0.9 days post-merger, everything is way too hot to have a strontium P Cygni. But if we just wait a few hours after that, 6 hours or so, then the ejector that's in closest to you will have undergone recombination. And so that part will be in strontium 2. And so you'll see an absorption profile. Now, you wait a few hours more, and then you'll also see it form in emission. But the absorption and emission are kind of detached in time. So the absorption emerges earlier, and then you have to wait for the light travel time effect for the more distant parts of the ejector to also undergo the recombination. So what I'm saying here is, no feature, then an absorption feature, then an absorption emission feature, due to this kind of sense that the electrons recombine, forming the element, but that they do so in different slices of projected velocity, each projected velocity being closer and closer to you, having a smaller light travel time, different physical time post-merger. Okay, and the cool thing is we have spectra to test every one of those statements. So 3 statements we're going to test. There should be no strontium P Cygni around 0.8, 0.9 days post-merger. 6 hours later, there should be a big absorption feature, but nothing in emission yet. And then around 1.4 days, we should start seeing it form in emission. Now, this was a prediction paper we wrote, me, Derek Watson, James Galanders, Casper Heinz. I will now want to turn to the data paper in which we have this unified spectral series to see if the statement actually ended up holding up. Now I'm going to plot here the strontium 2 fraction, like the amount of strontium which is in the strontium 2 state. It's a function of time post-merger, which depends, subtly on the electron density, not very strongly, and very strongly on this kind of temperature cooling in time, which will rapidly allow your electrons to recombine. There's a bunch of times we took spectra, and we can see how they fit with this emergence in time. If we look at the late time spectra, which people have thought about before, and here I'm defining late time as, X-shoot at 1.4 days or 2.4 days, we can see this big absorption feature, absorption emission feature. We see this full P Cygni in its full glory. Fine. But if we jump earlier, we actually get to see the birth of the feature. At 0.9 days over Australia, there was no feature, exactly as the prediction said. But just 6 hours later, by the time one took a spectrum over South Africa, a huge absorption feature has appeared here, which we can now interpret as being the absorption of the strontium 2 P Cygni forming. So we see this rapid onset of the strontium 2 recombining in the ejector. Now, the second half of my prediction was that we should be able to do the same statement for the equatorial ejector, right? But that has to do it about 10 hours later because of the light travel time effects. So it should be just around 1.4 days. Now, luckily, the X-shooter and the VLT took a spectrum at 1.43 days. Gemini and Flamingos 2 took a spectrum at 1.47 days. Those are only separated by 1 hour in physical time post-merger, but in that time scale, an emission bump forms around 1 micron, which is to say that the electrons in the equatorial region of the ejector recombine. And so we're seeing this thing forming in time on a time scale of an hour. A feature emerges and grows tenfold stronger in emission here. So it's very rapid evolution of the system. I also just wanted to point out one of the cool things about putting all these spectra next to each other is you can look at the earliest appearance of the feature, which means also when the thing is most optically thick at the outermost velocities, which means you're now getting constraints in the fastest line forming region we've yet ever observed in the kilonova. And here we're actually seeing a line forming region extend out to 43 or 45% the speed of light, which I find amazingly cool. And I want to also say that there's a bunch of models which won't produce this emergence in time. If you decouple your gas temperature just slightly from the radiation temperature of the blackbody field, you'll get a very different emergence in times at a very different time. And so you kind of very carefully have to match the observations now in what your model is doing. You also have to do this in a very particular way, which I like, which is the fact that we're seeing the recombination in the polar regions of the ejector probe by Australia and South Africa. We're seeing the recombination in the equatorial regions of the ejector probe by the different spectra in South America. Now, these recombinations are happening at the same physical time post-merger, around 1.3 to 1.5 days post-merger. Now, we observe them at different times because of the slight travel time effect, but the electrons themselves are recombining at the same time, meaning the line-forming regions in these different parts of the ejector are actually very similar, which kind of implies something about the uniformity of the radiation field in the line-forming region. So there's a bunch of things you can take out of this emergence, right? You can make a direct test of non-LT and LT line identifications. You test the very validity of approximating with LTE. You can test the assumption of the gas temperature being just the radiation temperature of the black body. I didn't even mention, but you're seeing a feature forming on the timescale of an hour. That puts a bound on the electron density, because if we know the recombination rate of an element, now we have a recombination time. In this case, for strontium-2, it's telling us that the electron density is 10 to the 8 or greater per cubic centimeter. It also is telling you, just from the different parts of the ejector undergoing a recombination, that there are no large temperature anisotropies between the line-forming region and the polar and the equatorial line-forming regions. But if there's one message you take away from this talk, then I'd ask it that be that when you see a kilonova spectrum, even though you take it at one point in time, even though that's taken at one point in time, that does not represent an object at one point in time. It extends across, great distances, and so one needs to take this reverberation or this temporal dimension into account when you start interpreting spectrum. Thank you.
Cool. Okay. Thank you, everybody.
Thank you very much. So, any questions for Albert? Yes. I think you need mic.
Thanks. Thanks for the nice talk. How sure are you that you're looking at strontium-2? Yeah, I'm just curious how you actually figure out what species cause the absorption lines in the spectra. Thanks.
Yeah, I mean, it's a great question. So I think there's many ways to answer this question. So I mean, basically every one of those paper I was enumerating shows you different ways of doing it. Now you can test why strontium-2 is such a good element. I mean, it's accessible. All of these lines are accessible in LTE, and it has some very strong oscillator strengths, which is to do with where you are in the periodic table. So I mean, strontium-2 also makes a few predictions. It predicts the existence of another line, which is this yttrium line around 760. It predicts this deprecation of the flux below 400 nanometers that James Galanders and Nick Vieira have been arguing for. And now you're also seeing that it kind of predicts actually down to the hour when the feature has to appear in time. So I mean, it's both from the modeling side of people doing radiative transfer, but also then you can make a few predictive statements.
Cool, thanks.
So any questions? Any questions from online participants? Let me see. Okay, let me ask one question. So you claimed before that from the strontium line shape, the ejector is quite spherical.
Yeah.
With this new analysis with a delay?
So I think, yes, sorry.
Oh, is that change your result, or you still think it's quite spherical?
So I think the sphericity statement is based on kind of two legs. One of the statement that we don't really understand what the origin of the black body is. And if it isn't intrinsically a black body, the kind of notion that you can make geometry statements from the emitting area falls down. So that's kind of separate from the shape of lines. The geometry statement here is somewhat to say that you need similar scattering in the equatorial regions and the polar regions, which might imply that you need similar amounts of strontium-2. But of course, you can tweak different degeneracies here. And this at least is showing that you need to be very careful about such an effect like reverberation, which can do it. I like the fact that reverberation, though, gives you an estimate of the temperature anisotropy in the ejector, because I think that's a bit of a different way of trying to probe anisotropies. But yes, one needs to be quite careful in modeling the line shapes and going from the relative strength of absorption emission now that we know that there are these effects that modulate.
Okay, thank you. So if no more questions, let's thank Albert again. Thank you. So next speaker is James.
unfortunately, we are actually missing two speakers from this session.
Right.
Because so James and Ian are not going to be here. So
Okay.
maybe we can just reorder the talks a little bit. So if the next speaker is able to come up a little bit early.
Okay.
Sorry about that.
So it's unfortunate, but okay. Next speaker is now Dongwen Tak. Yeah, he will tell us again the kilonova.
Good afternoon. I'm Dongun Tak from Seoul National University. And first of all, thank you for giving me an opportunity to present our recent work on kilonova, especially the promotion from the poster presentation to oral presentation. Oh, thank you. So today I'm going to talk about the impact of exact temperature and mass on the strength of the heavy element signature in kilonova. Kilonova is, as you know, highly energetic astrophysical phenomenon from the merger of two neutron stars. And there was great talk by Kenta and Albert in this morning. So I think you need the basic idea, but I want to briefly recap what is that. So kilonova is important because it is the origin of heavy element. As you know, to generate heavy element, we need so-called rapid neutron capture process, R process. And this process can be happen only in the high neutron dense region, right? And there's only a few sites where it can have the condition. And one of them is kilonova, and the observation of 2017 GFO confirmed that kilonova is a factor of heavy element. But still, there's a many question on this original heavy element because we don't know how much of heavy element are from the kilonova, and also the abundance estimate from 2017 GFO is slightly different from solar R process abundance. So we need to answer that kind of question. Then how we can understand the physics of kilonova. So here is the summary of the process behind the kilonova. So basically from the merger of two compact objects, it produced gravitational wave first, and then the relativistic jet launched for both jet axis, and within the jet, particle accelerated and produced gamma ray burst. At the same time, there will be relativistic ejecta around the center engine, and within such ejecta, R process nucleosynthesis occurs and producing the heavy element, and then radioactive decay of the unstable element power kilonova, and there will be a lot of bound-bound interaction. So to understand how this processes, you need to run full magnetohydrodynamic simulation, but it is very computation expensive, and also there are missing pieces like equation of state of a neutron star, and also it is difficult to reproduce observed spectrum. So our approach is just focusing on the last stage with radiative transfer simulation because it is more feasible and there's a handful parameters. And also we can reproduce observed spectrum. And from the radiative transfer simulation, we can estimate the amount of heavy element produced from kilonova, and also we can understand the ejecta properties of the kilonova. So there are 4 representative ejecta properties that affect the kilonova light curve and the spectrum: velocity, mass, and temperature and composition. For the first 2 parts, velocity and mass, will be talked by Lucas in the next talk. And I will focus on how the ejector mass and temperature affect the kilonova spectrum. So in order to do that, we perform radiative transfer simulation with TARDIS. So basic idea is assuming the photosphere, which emit the black body emission, and assuming there are a lot of photons from black body, we compute how much of line transition occur within line forming region. So basically, this blue one is photon spectrum that pass through the line forming region without any bound interaction. Okay. And here is barium-2 contribution. Basically, these photons have experienced interaction with barium-2. And if you sum up the whole contribution from many other heavy elements, you will get this black line, which is kilonova spectrum. So from this SED, we can compute the bolometric luminosity and contribution of line transition and also contribution from each species. So here is the bolometric luminosity in the temperature and ejector mass space. Definitely as temperature increase, the luminosity increase because our primary spectrum is black body. But as you can see here, at some point, luminosity decrease. It is because the line forming region is become optically thick, so that opacity increase, so that some photon cannot escape from the line forming region. And this figure shows the contribution of line transition. So you can see the hotspot here and wavy feature, and these are due to the neutral atom and singly ionized atom and doubly ionized atom, but I'm going to talk about in the next slide. So we compute the same thing for the four representative species. You can see the hotspots, right? We call this hotspot as a resonance island, where in this condition, for example, here, strontium shows high contribution to kilonova SED, which means it is easy to detect the kilonova features. Strontium feature in the kilonova spectrum. So strontium-2 has the largest island, which makes it easier to detect strontium feature in the kilonova spectrum. And in case of barium, it has isolated region. And in case of yttrium and cesium, there's a multiple island. Then why we have such island? Let's think about the horizontal axis first. As mentioned by Albert in the previous talk, there's an ionization, right? So as temperature increase, average ionization change. So in low temperature, most of elements are in the singly ionized state, but as temperature increase, it becomes doubly ionized atom. So that's why there is a boundary. As temperature increase, singly ionized mass of singly ionized atom decrease, so that there is less chance to have an interaction between photon and heavy element. And in case of vertical boundary, it is more complicated. So here is for fixed temperature, we just slice the island. As you can see, barium-2 show its large contribution before like cesium or strontium, but it decreased at some point. It is just because of the interaction of other element. If you assume only barium-2 in the line forming region, you will see the line becomes saturated and constant. But due to that other active element, there is more chance to interact with other element instead of barium-2, so that barium-2 contribution decrease. Then what about the multiple resonance island? So this figure shows the stacked SED. So if you imagine X and G axis, it is just normal SED. I just stacked it for a fixed temperature. And you can find the 3 hotspots. And the bottom panel shows the wavelengths versus ejector mass, and the z-axis is relative strength of the line. So you can see the three strong lines, and these are corresponding to these 3 hotspots. So basically, it means that the multiple island is due to the multiple strong lines within the element. In case of strontium, it has, okay, thank you. In case of strontium, there's only like 1 strong line, which is at around 1000 nanometer. That's why it has single island. Then what is the implication of this resonance island? To explore that implication, we picked the 2 points, one on the island and the other is outside the island. And for this condition, we changed the mass of barium and see how the spectrum change while fixing the other elements' mass. So clearly, as we change the barium mass, spectrum change, right? But outside of island, before condition, the change of barium mass does not change, does not resulting in any change in the spectrum. So this implies that one cannot constrain the mass of element if ejector condition do not agree with resonant condition of the element, right? Even though there is a barium there, but if, for example, total ejector mass is somewhere here, we cannot find the barium feature. Lastly, this is resonance island map. Basically, it is contour of 5% contribution from all elements. So, and we believe this is quite useful because, for example, if you observe kilonova with a temperature of like 6,000 from black body fit, then you expect the line signature from these elements, like doubly ionized lanthanide element, not from like barium or cesium. But if you're, on the other hand, if you find the barium-2 feature in your kilonova spectrum, then you can constrain the ejector temperature and mass, right? Because barium-2 feature is only prominent in this condition. And here is one example. This is AT 2017 GFO temperature and mass from calendar 2022. And from this curve, you expect that you will see the strontium feature and also yttrium and maybe cesium and barium. And as you know, strontium feature are reported in many literature, and also yttrium feature is discovered by Sniffen 2024. So that's it. So here is summary, and I will take question.
Thank you. This is great. So I was curious, there were a lot of claims for some of these like heavy elements in some recent like long short gamma ray bursts. Have you tried to like apply this to those? Like I think the work by like Andrew Levin and so on.
Oh, I haven't, but that's a good idea. Maybe you can try.
Cool, thanks.
You said you use the TAPDIS code to simulate this radiation transfer simulations. Do you use any other codes, or did you?
Yeah, I mean, I like to test other package as well because TAPDIS assumes some there's a strict assumption there. So maybe it has dependency on software, So we will test other software later. And also, the most important factor is atomic data, right? And there's a lot of uncertainty there. There's a lot of rooms to develop this kind of map.
Okay, thank you.
Sorry, thank you for the overview. This would of course be great to use, but I'm wondering how much uncertainty is there still in the basic physics of these transitions? Do we know all the basic physics that we would like to know before we start applying it and deducing things like temperatures, etc., in the ejecta?
Yeah, that's a very good question. As I said, the horizontal boundary is quite clear, but vertical boundary is less clear. But definitely it depends on like Einstein factor and something like that. That's electron density and so on. So I'd like to find some like mathematical forms that can explain that kind of features, but that's not quite mature yet. So thank you for the comment.
Thanks for the nice talk. I have one comment. So you said, although you said the horizontal direction is quite robust, but I think you need to check how much no LTE effect, I mean radioactivity, can change your ionization. So Saha is not always correct.
Yeah.
So
okay.
I think you should check which one is more important.
Okay, thank you.
So okay, let's thank speaker again. So so the next speaker is Lucas. He will tell us exploring the impact of ejecta velocity on the kilonova light curve.
I am Ji Lokusum at Korea Astronomy and Space Science Institute. This is together with Dong-Gun Tok and James Gillanders. And I'll be speaking about the impact of the ejecta velocity profile on kilonova evolution and the diversity of the kilonova light curves. I will begin with X-ray plateau in GRBs and introduce an ejecta model that deals with this radially stratified relativistic ejecta. And then in passing, I will also talk about the plateau in supernovae a little bit briefly, and then apply the ejecta model to the kilonova and explore the impact of the ejecta velocity profile and present the result. Okay, so there are two different astrophysical phenomena that occurs when two neutron stars merge. The first one is gamma ray burst, powered by the relativistic jet. And the other one is the kilonova, that's powered by the radioactive decay of R-process heavy element. And the jet propagates in space and interact with the ambient medium and develop relativistic blast waves. Blast waves. And that powers the emission of the afterglow, GRB afterglows. SWIFT was launched in 2004, and that surprised us with this observation of X-ray plateau in GRBs, this flattening phase in X-ray light curves. It was surprising because before the SWIFT, we thought that the light curve should decay in a simple power law fashion. In this Bloss wave, actually there are two shock waves. The forward shock, Fs, interact with the ambient medium and sweeps out the ambient medium. And the reverse shock, Rs, propagates through the ejected material. And one explanation for this X-ray plateau is to use the emission from the reverse shock. The reverse shock emission is dependent and controlled by the ejector structures since the reverse shock is going through it, okay? So now let me talk about an ejector model. So for a spherically symmetric ejector in spherical polar coordinates, the relativistic version of continuity equation takes this form. And here rho is the ejector density, gamma Lorentz factor, v is the ejector velocity, and time t and radius are from the central source. And then we were able to find an exact solution of this equation shown here by making use of Lagrangian description. In this Lagrangian description, the ejector is viewed as a sequence of infinitesimal shells ejected from the central source as a function of ejection time tau. Okay? And this tau plays the role of Lagrangian coordinates. So in each tau shell, we sit together and then we follow it and find its density there, which is moving with speed v. So in this expression, when v prime or gamma prime becomes large, this expression, density becomes very small. So it just means that when v prime is large, there is a large gradient between the velocities between shells. So these shells should spread radially, significantly, and that region becomes very low density. So that and that's expressed in this solution. Okay, here in this panel, the Lorentz factor of the ejector is shown as a function of ejection time, tau. And in the middle, there is a significant drop in the Lorentz factor, which means that shells there will experience significant radial spread out, and density becomes very small there, as shown here in this panel. And when the reverse shock goes through that region, the shock strength becomes small and the emission becomes small. And the light curve should respond to that, and the light curve will decrease. And when it recovers like this, light curve flattens. And this way, the reverse shock produces this flattening phase in the light curves. The plateau phase, plateau in supernova, on the other hand, is produced is due to a change in the opacity, right? So, as everyone knows. So the supernova shock waves ionize this hydrogen envelope, and that results in a significant increase in the optical depth to the electron Thomson scattering. And as the ejector expands and it cools, and the hydrogens recombine and become neutral, and the optical depth decreases, and then we are able to observe photons from outer shells successfully inward gradually as time goes, and that produces this flattening phase in supernovae. Then what about kilonova? So this kilonova emission is produced by the kilonova ejector that's expanding relativistically. So as in the case of GRBs, this kilonova ejector may end up with forming diverse density structures as it expands. And also this kilonova ejector is initially optically thick, so we cannot observe the emission. And as it expands and density drops and optical depth drops, and then we will be able to observe photons gradually from outer shells. So this kilonova case has something common with GRBs and also with supernova case. So some Plato-like feature may be expected in the kilonova light curves. So based on this expectation, in this paper, we applied the ejecta model to kilonova. And then here I show this kilonova ejecta velocity as a function of ejection time tau. Let's look at this pink model here. In the middle, there is a drop in the profile, which means that these shells will spread significantly, and then that will become a low density region. So that's shown here in this panel. Y-axis is the density of the ejecta and velocity. So in pink model has this low density region in the middle. If you look at this green model, in the middle area, these shells move together. So that forms this high density region in the middle. If you look at this yellow model, it drops initially significantly and flattens and drops and flattens. So the density has this structure. It is increasing initially and then drops and then increases again. So you kind of understand what's going on. So shells have different shapes of ejecta velocity profile, and those shells expands, and depending on their gradients between shells, they form different diverse structures within the ejecta. And now here I show the resulting light curves of these models computed using the TARDIS code. And as you can see, very diverse features in the light curves are produced. For example, here, steepening in this pink model, and flattening phase in this green model. And also some like Plato behavior feature is produced in this yellow model. And as you can see, these features are not there in all filters. I forgot to say that these different panels show different filters, U, V, G, V, I, G filters. The features are not there in all filters because this is of course because the optical depth here is provided by the line transitions with the heavy element, and that's dependent on frequency, of course. So let's try to understand these behaviors a little bit more. Okay. So let's look at this yellow core model. So I said initially the kilonova ejecta is optically thick, so we cannot observe it's opaque, and the photosphere recedes inwards as it expands. So initially the density increases sharply, meaning that scattering with the heavy element, degree of scattering will increase sharply. So light curve should steepen here at that point. And after passing through this maximum, density drops and the degree of scattering with the heavy element decreases and the light curve flattens there. And after this minimum, the degree of scattering with the heavy element increases again and the light curve steepens. So in this way, this density structure of the ejecta can leave its imprint in the light curves. So here I have the result. Here I talked about the Plato-like behavior in GRBs, supernovae, and kilonovae, and introduced an ejecta model that can determine the density structures of the ejecta for a radially stratified relativistic ejecta, and apply the model to kilonova. And kilonova ejecta velocity profiles can result in very diverse features inside it, and that can leave their imprint in the resulting light curves, the frequency-dependent imprint on the light curves. And future and current future observatories may observe these features, and those can be used to probe the density structures of the kilonova ejecta. Thank you very much for your attention.
Thank you very much. Any questions? Yes.
Hi, Lucas. You mentioned about this plateau phase due to this reverse shock. I wonder, I mean, if the energy injection model is somehow disfavored, or is there a way to distinguish between your reverse shock and the energy injection?
So that's very popular model. So if you want to produce this kind of a flattening phase, you have to hold the strength of the shock for some time. So if you inject more energy into the plus wave, forward shock will deceleration of the forward shock will pause some time, and that can produce this plateau phase. And that's very favorable model, of course. And then you asked if there is any way to distinguish between these two models. Both forward and reverse shock produce emission by synchrotron processes produced by these electrons accelerated into the shocks. So, and then we do not know those physical, the microphysical parameters in the forward shock and reverse shock. So one can fit observations using forward shock, also reverse shock. So it's not very easy to distinguish between these two models.
And do you know if people are also talking about like this energy injection in the kilonova afterglow scenario as well?
That's a good question. I think we should consider one can consider those scenarios also in kilonova case, and then that should leave some imprints and the like of course.
Other questions?
Hi, thank you for a nice talk. I was wondering, do you think that these features depend on the masses of the merging neutron stars, for example? Or like, could you reverse engineer the masses if you would observe certain features?
Right. So the amount of mass matters also, but what matters here is the degree of mass ejection loaded at between certain velocity interval, and that enters here into the solution through this m dot. So that also controls the ejector structure, of course. Yes, very good question. Yes.
Any questions from online?
I have a question.
Let me make sure. Yes, Albert.
Yes, thank you. Thank you, Lucas, for a very nice talk. So I appreciate the evolution with the variation in the light curve with density structures, but could you comment on it just to perspective how much this compares variation in for instance a nucleosynthesis abundance, if that varies across the ejecta? Is this big compared to those variations?
So that's my next project. I work on this on the light curve, producing light curves by including these heating rates, and then we want to find solutions and then present have the light curves. I don't have it. I don't have those yet.
Okay, cool. Excited to see that.
Thanks. Yes.
No more questions? Let me make sure that if online isn't there. Okay, so let's thank Lucas again.
Thank you.
And let's thank all the speakers in this panel session.
So apologies again for the fact that this session ended up being rather short. There were unfortunately some last minute absences, travel issues, etc. Now we thought that since we have an extra half hour, we might try to take advantage of it to have a discussion because obviously there's limited room for conversations right after the talks. And so we're happy to leave this open to the audience to decide exactly what to discuss, but just maybe to seed the conversation. One thought that seems to have passed through a lot of the conversations both yesterday and today is in terms of modeling, what are the best observational constraints on the models? And this applies both to, for example, the kind of population synthesis modeling of massive binary evolution that we heard about in the first 2 sessions yesterday, as well as, for example, some of the talks we heard in this session today. And one of the questions is, are there other kinds of observations that can perhaps be more constraining, or at least additionally constraining, not just the immediate observations that we're applying these things to? So to give you one example, yesterday we heard a lot of modelers discussing observations of massive binary evolution leading to gravitational wave sources, but we also heard, for example, a really nice talk from Kaushik, for instance, about using algols as an extra constraint, right? And this is very exciting because by the time we get to gravitational wave sources per se, merging neutron stars, merging black holes, the objects have gone through lots and lots and lots of different complicated interactions and different physics, right? We're talking about supernova and natal kicks and remnant masses. We're talking about mass transfer, stable mass transfer, unstable mass transfer, common envelopes. There's a lot of stuff, tides. There's a lot of stuff going on, right? And it's very hard. Of course, gravitational waves are a very useful constraint, but it's very hard to decompose all of those uncertainties and figure out exactly how to learn what happened just from the endpoints, from the rates and masses of the merging binaries, right? And so these kinds of intermediate steps are really useful. And the question is, what more could we do in that direction? What other intermediate constraints are useful? Are there other things that observers want to mention we should be looking at? For example, again, yesterday we heard a very interesting talk from Vivek about this neutron star, maybe a black hole, a very massive neutron star source in a globular cluster. Now, that's not going to emerge as a gravitational wave source, but nonetheless, it's constraining about the kinds of evolution we might be seeing in globular clusters. Similar things are applying, for example, to the session just now, in a different way, of course, right? We're not talking about population synthesis, but we're talking about, let's say, are there other environments that we can be thinking about that would be useful tests for, let's say, radiation transport issues, right? Because we have tidal disruption events, for example, where we have issues related to reprocessing. So there's something happening deep inside this Eddington envelope, and there is some reprocessing so that things look like far enough away. Of course, you have a photosphere of 20,000 degrees Kelvin or something in a typical TDE, but of course, that's not at all what's happening deep inside, right? And how do we properly account for that transport of energy from the inside out? Similar stories for, let's say, common envelopes in luminous red nova. Do those things, and oftentimes modelers work on one or the other topic and not on everything at once, right? So are there things that we're missing as modelers, and are there things that observers think that we can be using to apply better constraints, right? So this is, I'm intentionally leaving this very broad so that anybody who wants to jump in and contribute anything vaguely related, or just pick a different topic, please feel free. And I see Lika has a hand up, so wonderful.
Thanks. Yeah, I can obviously, or my comment would be on the modeling side, and also with when you mentioned Kurchik's talk, and on the binary interaction side, I think indeed, I think we all agree that these mergers have gone through some interactions, probably, at least if you think if they come from binary stars. But we really do not understand interactions well, binary interactions well. And I think one of the biggest showcases of that are Gaia black holes, where it's often kind of put away of saying like, well, but they're a different population because it's extreme mass ratios and it's all, it's all difficult. But we should really think, or I think it would be very interesting to think that there's also been low mass X-ray binaries for a lot of time. They're also extreme mass ratios. We've never managed to understand them evolutionarily. And then there's Gaia black holes that are all very extreme mass ratios, and it's uncertain whether they interacted or not. But we do know that Gaia, the last Gaia release is coming, and it will have a bunch more of these systems, not one or two, potentially like hundreds. So I guess my question would be, what do we need from the modeling side or from Gaia to use these kinds of binaries, these extreme mass ratios, low mass sector binaries, Gaia black holes as whetstones for binary interaction? Or to exclude something of saying like, well, if we stick to our old theory that they have such extreme mass ratios, they cannot have interacted, they will have merged. Or maybe is there something wrong with our theory of stable mass transfer?
Yeah, I agree much with that. And I would just add actually to that, especially with Gaia black hole theory, I think it was very interesting. That's like such a specific system. And I think beforehand, everyone was like, okay, this obvious has to be dynamics. But then there were, I think within 1 week, there were like 3 or 4 different papers where like half of the papers claimed it could be isolated, or like 50% chance it's isolated or dynamical. And then some papers that were dynamical. So I was actually surprised that it was still such a open, even from the simulation, like such an like system that's not clear which of these is more likely. And then I think the other system I would add is like SS433, which is also like maybe an extreme mass ratio system. So it's this like compact object that's hidden with a star where we see that it's been mass transferring, we think stably-ish, for quite a long time, like 30, 40 years or so. So I think it is actually why a lot of stellar evolution theorists at least were kind of claiming maybe mass transfer is more stable than before. At least is like the Ed van de Heuvel paper and so on. So I'm curious, like that should end up in our picture.
So that's a really nice point, Flor. And I'm going to channel Cole Miller for a moment. So a decade ago, at some meeting, Chris Bilczynski and I were talking to Cole about population synthesis work and modeling. And Cole said, don't tell me what you can reproduce. Tell me what you definitely will not be able to reproduce. Tell me something, for example, okay, if you're making predictions for LIGO, don't tell me what your predictions are for what it will see. Tell me what it definitely should not see in your models, because then once it sees it, I can come back to you and I can say, okay, something is wrong in your models, right? If you don't do that, and you have enough knobs to predict anything, then you're not actually predicting anything at all, right? If you predict everything, you predict nothing, right? So the question, I guess, is, are there things that we're confident being able to say that we cannot predict, that in the sense that, we don't expect this to ever come out of binary evolution, right? And I think as a community, there are very few things we're willing to do that on, but maybe Pablo is willing to make a bet. So Pablo.
So am I supposed to talk about things that are not possible, or what?
Yes. What is definitely not possible out of isolated binary evolution?
Well, that's one thing I was saying, more or less. Potentially, it's excluding spins. That's one restriction. But I actually wanted to bring something else that it's not exactly that, but I think an important thing that we can connect to is just high mass X-ray binaries. I think a critical aspect are the spins of high mass X-ray binaries like SIGX1 and 33X7 that are claimed to be essentially at critical rotation. And people are using this as an argument that they cannot be progenitors of LIGO sources. But I guess there's also a bunch of people that are more or less not that convinced that that is the case. And I wonder if it's also inconsistent with other things, like if SIGX1 formed a critical rotating black hole, did they also produce a GRB, for example, or something? So I don't know if through those areas as well, you can try and collectively use all this information for something.
More thoughts? No. Sorry, were there somebody else?
Yeah, just a follow-up thought on that, actually, that maybe we should start to see it the other way around. I agree with the papers. There's many papers around that, or there's some papers around that say, okay, maybe they're not, the X-ray binaries are not maximally spinning. But then I think still they say they must be somewhat like relatively high spinning, like higher than the gravitational wave spins that are inferred to be at around 0.2-ish right now. So I guess another way to thought that just popped into my head is there any reason why spinning black holes would be not spinning born black holes would not form gravitational wave mergers? Because that might be some way that we could say like, okay, well, but if black holes are at some point born with with a spin, we should at least see them occur to these gravitational waves. And I don't know of any reason why they wouldn't just show up in a gravitational wave. So maybe that's a way of excluding the birth. Though I know the spin measurements are very poor at this moment.
So maybe to bring in another topic. So Jean-Drew, you spoke earlier about sort of the, from a very theoretical perspective, right? What the signatures of the spin of Sagittarius A star might be. Would something like this provide a realistic constraint, for example, in any way on the spins of black holes and high mass X-ray binaries, right? Because we know that there are very significant systematic uncertainties in things that are coming out of, for example, continuum flux measurements or iron gallium reflection line measurements. And these are the kinds of debates that Pablo and Lieke were mentioning. So do we have a chance of getting at the spins in a different way?
Maybe. I haven't thought about it. What does the mission look like? I mean, are there resonant frequencies you can identify when you look at them? I mean, I would literally examine that and then see.
I mean, there are things that are called QPOs, right? Quasi-periodic oscillators, but I'm not sure that those would directly connect to your resonance frequencies. I don't know if people have all sorts of theories for what the QPO frequency might be, whether it has something to do with precession frequency, for example. But yeah, so I don't know if that's how that would connect to the resonance frequencies you mentioned.
I mean, it's a long time since I've looked at that. Like in QPOs, do you have like 3-to-2 resonances and 5-to-3 resonances and things like that? Because...
Sorry, Paul?
Sorry, continue, Jean-Drew.
No, I mean, I just don't have any data in front of me. If with the QPOs, if you can identify like frequency combinations that in your observation, then there's certain very clear predictions of like, I'd want 3-to-2 resonances, probably 5-to-3 resonant frequency combinations, and then I'd be able to say something. But
yeah, I was just thinking about your talk this morning and the application in X-ray binaries. If those resonances were set up, you would see it as, and there is a steady flow of material coming in, but they pile up, for a short period in the resonances and then move between the resonances, as you explained. You would expect to see something back in the light curve, right? Whether it shows up as a QPO or maybe even a more regular, periodic feature in the light curves. It would be interesting to actually look at that. In some of the white dwarf systems, we're actually trying to see this, but I'm not really sure if of course, you need another object or you need something to set up the resonances, right? So,
if it's a black hole, any perturbation will set up the resonances. Which one you set up will be dependent on the nature of the perturbation. So the reason why, I mentioned the 3-to-2 resonance in particular is that like gravitational radiation would want to open that one up more. And then the moment you have a 3-to-2 resonance matter that's collected into that, there's a 5-to-3 resonance just nearby inside it. So it's likely to ditch from 3-to-2 to 5-to-3. And so if you see that combination arising, you have at least some indication it could have resonant origin.
Sorry, there was a hand up, I think, online. Could we connect to that?
Can you hear me? I'm Balchandra Joshi. So this is a slightly different question to Jean-Drew regarding the resonances. So I was wondering that if you apply your your analytical formulations to supermassive black hole binaries. Do you think these resonances would have any impact on the dynamical evolutionary history of such systems? And if so, how would that affect the low frequency, the nanohertz gravitational wave spectrum?
So, I mean, my analysis is very much in the perturbative regime. So you need to have a big black hole and a smaller one. When the two masses become comparable, even like 1 to 10, I mean, I'm not saying anything. I think Harold Pfeiffer did actually go and look for resonances in the most extreme mass ratio numerical relativity simulation they could at the time. And he didn't see it, but he was only looking at like 1 to 6. So only in the situation where you have a big black hole with a small perturbation around it is my analysis strictly valid. I mean,
So one of the candidates, OJ287, if I remember correctly, has a 1:10 mass ratio, billion to 100 billion solar masses. So which would sort of fit in the kind of thing which you are saying. And the model there says that the smaller black hole plunges through the accretion disk twice as it goes round. So there is a perturbation also in the accretion disk, but I don't know whether that would tie in with the resonances which you were talking about.
That would be interesting. I mean, depends on where it's plunging through, or also how many M it's plunging through. If it's close, then maybe. But you must know that the moment it's got a mass of its own, it's going to make, just like, I mean, if you go back to the example of Saturn's rings, right? Some of the ring structure is originating from the dynamical modes of the star, and then there's very distinct clear lines that they've managed to identify with orbital residence with Saturn's moons in itself. So it will be a more complicated system. My nice, pure, clean game will no longer work as well. But it might be, at least looking at a modification of it might be worthwhile.
Okay, thanks. Yeah, that's an interesting point to consider.
I mean, another one that might be in the same direction, but more extreme mass ratios is QPEs, not to be confused with QPOs, so quasi-periodic emitters, but for which one of the models is that it may be a star that's being partially disrupted while going on a essentially gradually spiraling in and being on an extreme, it's an extreme mass ratio system, spiraling into a supermassive black hole, or maybe plunging through an accretion disk, and you're getting the emission when the star is crossing the disk. In some models, it's even a stellar mass black hole that could, rather than a star, that could be doing the motion around the supermassive black hole. So there are a variety of models around, but many of them have this Emery character, albeit perhaps with a much lower eccentricity than a typical Emery.
That might be an interesting avenue to explore. Thanks.
More thoughts, comments? Yes, Paul.
Yeah, switching topic a bit to the spectral evolution modeling. I was very happy to see that Lucas was actually putting the curves, the light curves in the different filters up there, because that's one of the things that observationally we can provide, and it is actually interesting to see that even in the different models, right, for a given shell structure, the light curve is very different from these bands that are quite nearby in the optical. Basically, the question is, from an observer's point of view, which types of combinations of colors or bands would be most informative to decide between various between various models, for instance, the shell structures or the continued ejection, etc. So thinking more from an observational point of view, what is it that you would like to see us provide to be able to model the ejecta better?
Does anybody want to take a stab? Go for it.
So the light curves produced are also dependent on the abundances in the ejecta. So that determines the opacity in different wavelengths. So it's also model dependent. Once you fix the abundances, you have these light curve behaviors, and then you can maybe compare this A band and B band, and then take a ratio of these two light curves, and then look for some features in observations also. Something like it's possible, but that's also model dependent. And from the side of the modeling, I assumed that we have this kind of dense velocity profile. That's assumed because we do not have much clear idea about the kilonova ejecta velocity profile at the moment. So I hope that these numerical simulations of the binary mergers can produce more like a concrete ideas on what kind of ejecta structure or velocity profile or mass ejection rate as a function of ejection time is expected.
Oh, sorry. Sorry, Kent, I was looking up instead of down.
Yeah. So I can do a few more things. So there are several characteristic wavelengths that we are interested in. For example, if there are first peak elements, we expect so many lines around 4,000 to 5,000 angstroms. So the luminosity there is very sensitive to the abundance of them. And as we learned from Albert, around 8,000 angstrom, there is strong strontium feature. So that's also can be seen in the photometry. So that's information interesting. And also another interesting thing is around 2 micron, I believe it's K band. That's also, we expect some emission line there. So yeah, photometry definitely will be quite useful.
Yeah, of course.
You're getting a workout today. So this is very interesting because I noticed that in the astronomical and the observational community, optical, there is a tendency to think, oh, kilonova will be red, so we only observe in the red bands, right? So in R and I and Z and stuff like that. But basically, what you're saying, Kenta, is that it's extremely informative to also be looking at in those blue bands below 5,000 angstroms. And in the red bands, because the contrast should be very large, and therefore that is actually maybe even more informative than just only in the red bands. Can I summarize that correctly? Yeah, very interesting. Yeah, and 2.2, sorry, 2.2 is of course infrared, right? So, but I think the next binary neutron star system will be observed to death, basically, like the first one, because we waited for so long. So I don't doubt that all the infrared instruments that we have will be put on that. My hopes for LSST. Oh, okay. Can I be controversial? Is that okay? LSST is too slow. So, unless it's a dedicated program, which I'm sure that they will do, right? But it has to be fast. So fast and multicolor. But especially the bluish, right? So the U band, which is not that common. Of course, there's a different instrument that I happen to be PI on that actually does have it. I think that's why I want to emphasize that it is so important to actually get all those different bands, just to make sure that we have that information instead of then being in the dark, literally still about what happened there.
Sorry, there's another comment from online. Albert?
Yes, I just wanted to add to Kenta's statement here. Not only do I think that all of those photometric bands are super interesting, it's also really a question about cadence here, because we're seeing, that there are specific times where some features will form and they can do it on a timescale that's as short as an hour. And if you can narrow that time interval in, you don't just get a nice line identification, you get the temperature of the particles, you could get the electron density. So like you can get to a lot of physics if you get to a very nice cadence. And there are specific intervals in time where that becomes interesting at specific wavelengths. So there's a lot you can actually optimize for.
So what is the reasonable and achievable combination of instruments that you would need? For example, it's from your talk, right? You were mostly discussing ground-based observations, right? But because, okay, it's hard to imagine that you're going to get 1 hour cadence with JWST, even on a kilonova. But what would you actually need and what is achievable?
Yeah, so of course that depends entirely on what feature or thing we want to optimize for, right? So if we're going into the near infrared and it becomes something nebular, then of course we don't need a very high cadence. But if we want to see these recombination waves in the ejector, then we're talking about something optical from the ground. But I think it's a subtle point that like over 35 minutes we can see features becoming several fold stronger, and getting that narrowed down in time is actually really informative for modeling.
Oh, sorry.
Maybe sorry to dominate this, Albert. Thank you. But I think also in the GW follow-up community, we're still a little bit stuck in the old GRB thinking of saying, okay, you know, our cadence can be lower as the event ages, right? So at the very early times, you want to do basically continuous observations, but a day after you can already relax a bit, and 10 days after you can come back basically once a day, etc. Are you saying that we shouldn't do that because there could be episodes where there's still rapid evolution, even if it is, say, 3 or 4 days after the event, and that we should try to keep up the cadence as high as possible, basically?
Yeah. So I think I am making the point that there are specific intervals in time where it's super exciting. So for instance, for us, there isn't actually a lot of information between going from 12 hours to 24 hours in the kilonova, but there's a bunch of stuff that happens from 24 to 36. So that's, there are specific intervals. I don't care about a high cadence around 3 days, but I would really care about, those few hours around there. So it's, but of course, that depends upon the ionization energy of the specific element, and we don't know the diversity of these objects. But yes, there will be specific intervals that are particularly exciting.
So actually a question, if I may, following up, sorry, I have the microphone, so I'm going to ask, if I may follow up on the diversity question, and this is also something that Kenta mentioned during his plenary talk this morning, which is that actually, as far as we can tell, a lot of binary neutron stars that we know of in the galaxy are kind of sitting right around the threshold for various things, right? They might be sitting around the threshold for forming a significant disk. They might be sitting around the threshold for, the division between the supermassive and a hypermassive neutron star, for example, at the moment of merger. They might be sitting around, therefore, the threshold for whether or not you're able to form a GRB in a jet. So does that mean, and perhaps it means that also are sitting around the threshold for how much R-process nucleosynthesis they're actually able to generate, and how much chemical enrichment they're able to do. So does that mean that since we're kind of, nature has decided that we're sitting right around the threshold, does it mean that we cannot be necessarily guided by previous observations for what the next one will be, because the next one is a tiny bit more massive or a tiny bit less massive, for example, the mass ratio is a little bit different from Unity, then the signatures and the time scales might end up being quite different?
I mean, I would say we don't know yet, right? I mean, the models for something which is subtly closer to the mass of prompt collapse is an entirely different nucleosynthetic output, right? So we don't know. I mean, the ones we're talking in the literature, at least if we want to sample, we're talking photometry, right? And I think it's remarkable how similar in photometry these transients have been looking, but again, that could be a selection effect for what you're searching for. So I don't think I have a satisfying answer. I would say, though, we can still inform when we want to look at it in time, because if we have a few photometric points telling us what temperature it is, we should still know, how fast it's cooling in time, and then we can guess when we should be keeping an eye on the object. So we can use the earlier observations of the objects we're getting to inform when we want to look at it in the future.
Yeah, that is exactly what we want to know. I mean, this is sort of the field of neutrino radiation transport. So now we understand that a little bit change in the total mass, a little bit change in the mass ratio, the distribution of the element changes. So we want to test this with the future observations, that if you change a little bit of mass and how the kilonova look like, and different viewing angle as well. So we are really desperate next event.
So maybe this is a good point to, oh, sorry, Samaya wanted to make a comment, please.
Yeah, I just also wanted to mention to the audience, as well as to hear Kenta, as well as maybe Albert's perspective, that we do have UV satellites, such as Ultrasat, as well as UVEX. And one of course, the major science goals of Ultrasat, which is a wide field UV satellite, is to go after the electromagnetic counterparts of gravitational wave mergers, as well as UVEX itself. And of course, the aim is to try to do that as soon as possible to really try to ascertain information about the kilonova itself, as well as how the jet possibly interacted with any ejector material. And I wondered if I could hear Kenta's perspective about what you're excited about on the kilonova side, as well as Albert, with those early observations, not just from the ground, but obviously with these upcoming missions.
Albert?
I don't know if I have anything particular to add. I think the few Swift photometric data points we got in 2017 are really, remarkably nice for modeling, because it gives us a good understanding of the radiation field in the ultraviolet. You'd need, I guess with the rate you're fading, it's a very early time constraint we're talking about. So I'll leave it to Kenta.
Right. Yeah, there are some simulation about early UV emission, but we don't know really that calculation is okay. So there's different regime. So in the UV with heavy elements, just so many lines, maybe our approximation wouldn't work. So I think UV will add more information, and definitely from the GW17 or 17, at earliest time, the spectrum at least continue to the blue side. So it's not necessarily faint. So I think it's Ultrasat gonna be very interesting.
And I think it's worth emphasizing at least that our radiation modeling does not look like the UV side of the spectrum. It's a very nice extension of the continuum at early times. So there is something missing in our continuum modeling, which is, I think, exciting.
So maybe this is a good point to wrap up. First of all, because we're hitting 3 o'clock, but also because we are ending on this note of some optimism, as well as an admission of challenges. Namely, there's lots more modeling work to be done, but also an excitement about various upcoming observations across a broad range of wavelengths and even types of observations. So lots more to talk about in the afternoon. Okay, Flor, you go last.
Sorry, I just wanted to maybe add one ending note, which is also, I think it's also important. I think something that we're really realizing from all these conversations and the different talks is there's all these different communities in gravitational wave astrophysics that often don't talk to each other, like radio, meerkat, observations. I think it's really hard because it's such interdisciplinary. So maybe one thing we should also do as we take this break is think about how do we involve different communities, also earlier career people, like a lot of the people who haven't spoken so far. And especially people when there's limited funding for a lot of people at different institutes to attend international conferences. But yeah.
All excellent points. Thank you. All right. See you back here at 3:30.
And finally, I will summarize and conclude our results. Finally, black hole mergers dominate the type of gravitational waves measured by the LIGO Virgo Kaga experiment so far. Nevertheless, the astrophysical environments of such coalescences remain unknown. If measured, radiation signals accompanying these gravitational waves
Can we maybe have the slides of the first presenter already on the screen? Thank you. We'll wait a few minutes until all the people are back. I can hear a lot of voices in the back. All right, feel free to. Welcome back, everyone, to the final session of today with a great set of diverse speakers and talks. We'll just start. And so, yeah, please go ahead.
Okay, so good afternoon, everyone. So thank you, organizer, for having me today. I'm Hiromi Shitagawa, working at Shanghai Astronomical Observatory, and these are collaborators working on this topic. So today, I'd like to talk about the evolution and mergers of compact objects in AGN disks. Especially, I'd like to explain about the observational understanding of these systems and the properties of AGN disk structures and mergers in this environment, and also the possible electromagnetic counterparts to mergers. So let me start from the introductions. So the main motivation is the detection of black hole mergers by LIGO Kagura. We haven't understood how these black holes have merged. And I'm mostly interested in the AGN disks because many things can be happening in this environment, and these systems are poorly understood. So I think that it is very nice to understand this system more using gravitational wave observations. And to understand the possible event originated in the AGN channel, let me explain how black hole merges in this environment. So in this channel, we consider the environment in the vicinity of supermassive black hole, where there are dense stellar clusters and geometrically thin, optically thick accretion disk. And once they coexist with each other, compact objects and stars in the nuclear star clusters are gradually captured by AGN disk. And also outer regions of AGN disk is gravitationally unstable, so stars and compact objects can form as a result of their evolution. So these are the typical theoretical predictions. And there are also observational supports on this picture. So these are the projected distribution of the stars in the center of our Milky Way. So right panel shows the S stars, and left panel shows the OB and Wolf Y stars in clockwise disk configurations. And this distribution can be well explained by the capture of stars in nuclear star clusters by AGN disks, and star formation in AGN disks, respectively. And also there are another interesting observation, which is spatial distribution of low mass X-ray binaries. So Sheehan plots represent their spatial distribution in the center of our galaxies. And this distribution can be explained by the binary formation within agent disks. Although these models haven't been concluded robustly, but these observations anyway suggest or support the scenario that the compact objects or stars are captured or are formed in agent disks. And if we believe that the compact objects are embedded in agent disks, we can predict how they evolve within the agent disks. And to consider the evolution, it is important to understand the structure of agent disks, concerning the outer regions where gas is gravitationally unstable. So currently there are several models. So let me explain the possible models. So Silko and Gutmann first proposed that the outer region can be stabilized by unspecified heating source. And later, the Thompson et al. Found that this region can consistently stabilized by the in-situ star formation. And recent work by Gilbert and Stone suggests that these regions can also stabilize by stellar mass black holes embedded in agent disks. But in the reality, both the star formation and stellar mass black hole would contribute to stabilizing the disk. And the student in the Columbia University, Epstein Martin Margherite, models the evolution of the disk structures, considering the time-evolving feedbacks from stellar mass black hole and in-situ star formation. And this is the evolution of the number of stellar mass black holes, and different color represents different inflow from the outer regions. And we consider the Milky Way like AGNs. And we can see that many compact objects actually form in the usual AGNs. And these compact objects can evolve within the agent disk and merge with each other. And to consider the possible evolution, it is important to understand whether gaps can form within agent disks, because mergers are frequent in such regions. So next, let me show you whether gaps are expected. And to consider the possible gap formation, I'd like to consider the aspect ratio distribution, because gap forming criteria is very sensitive to the aspect ratio. And the left panel shows the starburst only and stellar mass black hole only models, and the right panel shows the starburst plus the black hole models at different phases. And we can see that there are low aspect ratio regions, and in such regions, gaps are expected to form. And such formation is found independent of the mass of supermassive black hole and viscous parameters. And this is because in moderately outer regions, there are low temperature regions. And in such regions, there are no ionized hydrogen and dust. So opacity of the disk becomes very low, and the optical depth of the disk becomes also low. Then the radiation pressure onto the disk becomes very, very low, and high gas pressure is required to stabilize the outer regions of agent disk. And such high gas pressure is realized for high gas density and low scale height of the disk. So this is why there are low aspect ratio regions. And in such regions, compact objects are accumulated and mergers are frequent. And I'd like to also note that in Silko and Gutmann model, they post the lower limit in several variables, which unphysically suppress the gap formation. So if we believe the formation of gaps, we can understand how compact objects evolve by performing the n-body particles by considering the gas and stellar mechanisms. So by performing several simulations, we predicted how the properties of merging mass and spin are distributed. So these are the sharp and primary mass distribution. And this distribution is well characterized by hierarchical mergers. And I'd like to also note that the accretion is kept at the Eddington rate in these models. And this distribution is somewhat consistent with the observed distribution, and spin distribution is almost isotropic due to the randomization binary angular momentum direction at binary single interactions. And the rate is also roughly consistent, although it is highly uncertain. So currently the contribution by AGN channel is highly uncertain. So to find the possible event contributed by AGNs, we need to find some signatures. And other signatures, I would think that the electromagnetic counterparts are very useful because other channel cannot produce such emission, but AGN mergers possibly produce some emission due to the rapid accretion. So let me explain several possibilities that the emission is associated with mergers. So associated with compact object mergers, we can expect two types of energy injection, which are jet and explosion. But in the case of black hole mergers, we can expect jet production associated with shocks forming in the circumbinary disks due to the caused by the recoil kicks at the mergers. And such jet can collide with several components surrounding the merging binary, which are the AGN disk, wind, and circum black hole disks. And we can also expect several kind of emission. For example, breakers emission is emission from the shock front, and the shock cooling emission is emission from deep inside the shock gas, and non-thermal emission is emission from accelerated particles. And here I'd like to especially focus on the shock cooling emission from AGN disk and wind, and breaker emission from circumbinary disks, because they are very bright in the optical and gamma ray bands, which are relatively easily detected by wide field surveys. And interestingly, this emission can explain the optical and gamma ray emission possibly associated with the most massive and fast gravitational wave events. So these are the SED, and the solid line represents theoretical prediction, and the red point represents observed flux. So I would think that this is interesting possibility, and to test these models, we propose that there are moderate color evolution and preceding X-ray emission to optical emission, if these models are correct. So these are nice to be tested by future observations. And finally, I'd like to also note several possible signatures. So the higher eccentricity for massive binaries, Doppler acceleration, and spatial distribution can be a strong signature of AGN mergers. And the ranging of gravitational waves by supermassive black hole or third body can be a very interesting science, although it is very rare. And some correlations are also useful to find the signatures. So these are all nice to be investigated in the future observations. So this is a summary slide. So I think that black hole mergers are AGN channels are very promising environment for black hole mergers and electromagnetic counterparts, especially the optical and gamma ray emissions are very interesting signatures for mergers in this environment. So these are nice to be tested in the future observations. Thank you for your attention.
Thank you very much. I'm sure there are some questions that people have about this super interesting talk. Okay, see, it's many. Okay, I'm gonna run.
Hey, thanks for the nice talk. I'm curious, in the signatures you're talking about lensing, but there's a lot of people working. I think you're talking about some form of self-lensing. from the supermassive black hole that's located right there, right?
So I'm concerned that the lensing by supermassive black hole.
Okay, because there's a lot of people working on lensing by galaxies in between or clusters, or so I'm curious, weren't you expecting this case, if you see a lensed gravitational wave, that you could also see a lensed AGN and make a connection in that way, or are the chances of that happening negligible?
Oh, do you mean the lensing of electromagnetic emission from the host AGN?
No, I'm saying more or less, imagine seeing an Einstein cross and more or less you have an AGN that's being lensed through that in multiple images, and then it happens to have a black hole merger. Then you would see the black hole merger lens as well. It might be a bit too exotic.
Oh, sorry, maybe I couldn't understand, so
I
let me
can check
discuss
back
it
afterwards.
later.
Thanks.
So I have a general question about counterparts from these black hole mergers. And this is something that I admit has always bothered me, which is that long before the merger, right, you already have two black holes that are moving through a disk with lots of gas. They're probably doing some accreting. So there's already a source of radiation. And in fact, in some ways, when you kick the black hole remnant, if anything, its Bondi radius, for example, will drop because it's moving much faster. So why is it that this should lead to an enhancement in the overall radiation, right? Because the Bondi radius drops, there's actually less accretion happening onto the black hole after merger than there was before merger.
Yeah, so that's a tricky part, but we actually consider several scenarios. So in the previous scenario, we consider that the jet is produced even before the mergers, which creates the cavity regions. And after mergers, jet direction is reoriented, which can produce additional shocks and produce additional emission. But in that case, gas accretes significantly, so which would be inconsistent with some observations. Another possibility is the associated with mergers, the accretion state changes due to the shocks forming the circumbinary disks. And such shocks can realize the relatively low angular momentum gas flow, which enables a highly Eddington accretion, which is consistent with tidal disruption event and X-ray binaries or something. So.
Great. Are there any other questions? If not, I also have a question, which is like, so you mentioned like some of the gravitational wave sources that maybe had associated EM counterparts. Can you remind us like what was the probability of like it being associated with those gravitational wave candidates in those cases?
Yeah, that's the highly uncertain and yeah, lower limit would be 0, and I think we can also consider the upper limit, which would be so first, if the AGN is type 2 galaxy, we cannot see emission, and also if jet do not collide with some components, we cannot see any emissions. And in the case of gamma ray, we would expect some beaming, so the probability is reduced significantly. So generally not so high, but it is not a constraint, and yeah, hopefully it would be high, but
cool. Yeah, I think there's time for one more question, and while you can think about that, I ask if Nigel can already come forward. So you have a question, or you? Yeah. Can you already come forward, or like maybe get the microphone set up? So you have to go actually upstairs and set up your microphone. But there's, in the meantime, so we're skipping Jordi's talk, which is scheduled because I think he's not here. But there's time for one more question, and so please, if someone has. You can ask it now. Otherwise, I'll ask one, but I'm sure there's someone in the room who has a good question. I just look very awkward to everyone. Okay, you have the chance to ask. You can think of questions for the next talks. But I actually have something I wanted to ask you, which is you showed the mass distributions of binary black holes. Expected. It's not on the screen anymore, but it's okay. Like chirp mass distribution of black holes from this channel. But do you know, is it possible to make a redshift evolution of the black hole mass distribution? Like, can you make a prediction for like redshift evolution for this channel, or is that difficult?
So one of our collaborators, Yang et al., predicted the mass distribution, assuming that we estimated the merging rate distribution evolution.
As a function of redshift?
Yeah.
Oh, that's great.
So we just assume that it follows the AGN density distribution.
Okay.
As a function ratio.
And that one is known from observations, and like you have some intrinsic, like assumption or what the intrinsic distribution of AGNs is based on that.
Yeah. Yes.
Oh, that's very cool. Okay, I think Nigel's done. Let's give a big applause and thank you for your nice talk. And I think we can try to put the next slides on the screen. Thank you. And I would especially encourage, like, if you haven't asked a question yet in the past days, try to come up with one. We really want to hear from everyone in the room. Yeah. And so if you're the speaker of the next talk, you should kind of go up now-ish to like during the talk of the previous speaker to get the microphone working. Thank you. Do we have the slides for Nigel? Ah, great. Thank you. Perfect. Thank you. Take it away, Nigel.
Good afternoon, everybody, and I'd like to thank the organisers for this opportunity. So what I'm going to be talking about is some joint work with the colleagues shown there, Monas Naidu and Piet van der Walter at Rhodes University, and Vishnu Kakat and Amos Kubeka at UNISA in Pretoria. And what I'm going to do over the next 12 minutes or so is summarise these 7 papers. So if you're interested in what I've got to say, please just search for my name on arXiv GRQC and you'll find those papers there. Okay. All right, so let's start really with what I might call the prior state of knowledge concerning gravitational wave interactions with matter. Well, in a way, it all goes back to 1957 when Feynman gave his famous thought experiment about a ring on a stick, showing that gravitational waves do carry energy. All right, and the gravitational waves can interact with matter and thereby transfer energy from the waves to the matter. Right, and the theory of gravitational waves developed very rapidly after that. And in 1966, there was a paper by Stephen Hawking, which wrote down this formula here, which is really relating the gravitational wave outside as it goes through some matter. So that just pass, if you've got some matter of thickness delta, then the wave gets diminished by a factor x minus 8 pi eta delta, where eta is the shear viscosity. Delta is the distance that you travel. Now that looks like a lot, but then you've got to translate that from geometric units to SI, multiply by G over C cubed, and you get 10 to the minus 36. All right, so when one starts putting in the numbers, I mean, even though astrophysically viscosity can be quite large under special cases, and cosmological distances are very large, in every scenario one can think of, when you put the numbers in, you get out that something's absolutely tiny. So I'd say for about the last 60 years, the attitude within the gravitational wave community has been, yes, gravitational waves do interact with matter and do give energy to the matter, but the effect is so tiny you completely forget about it. And that's been the attitude for a long time. And what we're going to show is that, yes, generally that is the case, but there are cases when that does not apply and that the effects can really be astrophysically significant. Okay. All right, so the formalism that we're going to use is the Bondi-Sachs formalism, where your system of coordinates is based on outgoing null light rays. Minkowski space-time, and this is a completely general metric, and Minkowski space-time is given by putting nearly all the parameters equal to 0. And HAB is then just d theta squared plus sine squared d phi squared, the standard unit sphere metric. And we'll write down metric coefficients to be of the form a spherical harmonic times something that's sinusoidal or cosinusoidal in time. U is the time coordinate in this language. Right, and the f of r is a complex quantity in general, and the real part gives you the cos nu u, and the imaginary part gives you the sin nu u behavior. So this is a very standard separation of variables ansatz, and you substitute into the linearized Einstein equations, and everything cancels out, and you get a system of ODEs, which you can actually solve, and you end up with solutions which are polynomials in 1 over r. And that's actually very nice because polynomials in 1 over r are very easy to work with algebraically. All right, I'm defining the rescale gravitational wave. So it's rescale. So you put the r outside so that it doesn't diminish as you go, as r gets larger. You can write down the gravitational wave strain takes this form. Okay, so then the model that we use is we have 3 solutions. We have a source, we have some interior solution, we have a thin shell, and we have an exterior solution. And paper 1 that I showed you is really all about how you glue those 3 solutions together. And I won't go into any of that. All I'll do is ms is the mass of the shell, and I'll write down what comes out of that paper. So the first thing we looked at was the modified gravitational wave strain due to a dust shell. So there's no viscosity, it's just pure dust. So there's no energy transfer. All right, and we find that H is modified in this way here. So when the mass of the shell is 0, there's no modification. So the first correction term represents gravitational redshift. So fine, we know that. Second correction term is nu. It's out of phase with the leading terms, therefore changes the phase of the wave without changing the GW energy. And the third correction term represents a partial reflection of the wave by the shell and leads to the possibility of an echo. So when we did this in 2019, there was talk about gravitational wave echoes from GW 150914. That's gone. So that's why we were particularly interested in that at the time. Okay. Now what I want to do is to just give an example to show that these effects are not negligible at all. They're not large, but even for a dust shell, they're not negligible. So what we've got here is 2 curves. The original signal is in blue, and that modified by the dust shell is in red. So if you've got highly accurate, if you've got an event that takes place nearby, you would be able to distinguish between those 2. Okay, the measurements could. So this is, for example, of a supernova and how the signal would be modified. Okay, so that's really the only point I want to. I mean, obviously, the uncertainty in modeling the supernova far exceeds the difference between those two curves. So it's not going to tell you anything physical, but it's just to show that the differences are not tiny. All right, now move on to viscous damping. All right, the gravitational wave energy from GWs to, we use this formula here, where eta is the dynamic viscosity, and RO, the inner and outer radius of the shell, and the relation between HR0 and HRI is given here. All right, and it's to understand what this, all right, so what this means, it's useful to look at two special cases. First, the short wavelength approximation, when lambda is much shorter than the radius of the shell, then essentially all these terms here disappear and you're just left with the first term. And that's what Stephen Hawking produced 60 years ago. Okay, but then look at the other case, which is the long wavelength approximation, where lambda is much bigger than the radius of the shell. And essentially all these terms are going to become unimportant. And what you get out is just the last case. And if you're talking about a shell that goes from R equals, say, Ri to 2Ri, essentially you can forget about that 1 minus alpha to the minus 7. And you end up with this formula here. And the point is that lambda over Ri, all right, if it's largish, and then you raise it to the power 7, you can get something that's quite big. And that's what's really behind this. So, and then the corollary of if the gravitational wave loses energy to the viscous medium is going to get hotter. Okay, and then this is just writing down the formula for that. So this will involve some additional physical constants, the specific heat capacity, the density, and the energy of the gravitational waves. The energy doesn't come into this one here because we're just talking about the ratio between out and in. So the energy can be whatever it likes. It cancels out. All right, so now what I want to do is just go quickly through, very quickly, just through some examples. Right, so this is parameters from a core collapse supernova. The reason why these values are chosen are all discussed in the papers. They're all taken from the literature. All right, and I mean, what we get is a tremendous range for the temperature because there's such uncertainty in some of the values. It can be either completely insignificant to highly, now nothing's going to increase by 10 to the 20. That's just what this formula says. If you're getting a large increase, there will then be other physical effects that will come into play to disperse that temperature. But I mean, what that's saying is if you're getting out a large number, then it needs to be taken into account in the modeling. And for the gravitational wave damping, I'd like to show this figure. What this has got is the radius of the core varying between 10 to the 4 meters to 3 times 10, right, 10 kilometers to 30 kilometers. The frequency of the gravitational wave from 100 to 1,000 hertz. And this is on a log 10 scale, the viscosity. And what we've plotted is the surface for which the damping is exactly a half. And because you're on a log 10 scale, if you're a little bit above it, it means that the damping will be almost complete. If you're a little bit below it, it will mean that it's almost negligible. So you can see that, I mean, for low frequency, low radius, even at viscosity at 10 to the 15, you would get significant damping. All right, so in a way, Ilya asked people to make specific predictions. So if we do ever see a nearby supernova, here's a specific prediction. We probably won't see any gravitational waves from it. And if we do, they'll only be at the higher end, 1,000 hertz. All right, we also looked at a model of GW 150914. If there's matter around an event like that and just took out those numbers from there. All right. I mean, of course, it's unlikely that matter is going to be around, although that one, there was the gamma ray burst that was detected by Fermi, but not by other detectors, so who knows? So the resulting temperature increase works out to be of the order 10 to the 6 degrees K, which is not enough for a gamma ray burst. And the GW damping effect is absolutely negligible. I mean, it's really because there's such a huge amount of energy. You just need a tiny amount of that going into the material, and you could have a significant temperature increase. Then the post-merger signal from a binary neutron-star merger. In this case, we get out that the effects are going to be highly significant, whatever. Okay, the temperature increase, which isn't real, it's just an indication that the transfer of energy is important. And the GW damping varies. I mean, normally when you do this, you get H is between 0 and 1. What it's telling you is that unless you're really at the parameters really at the limits which absolutely minimize gravitational wave damping is going to be significant. So here's another prediction. We won't see post-merger signals, or if we do, it will only really be at 2000 Hertz at the upper limit. All right, and then finally, a little on primordial gravitational waves. Okay, this is last slide. So 2 aspects to this. At the end of the inflationary era, there's the idea that primordial waves were produced, taking values from I mean, this is so that then when you translate to what's observable now, you get waves that are detectable. Okay. What that would say is that they're not going to be detectable. They would be completely absorbed, even if the viscosity is as low as that. On the other hand, the electroweak first order phase transition, which happens a little bit later, and is predicted as a source for LISA, at emission would be 10 to the minus 4 meters. It's I can't remember, but it's a few millihertz at now. We find that the damping effect is negligible, so that would still be seen. Oh yes, this one. I just want to say, if we change the this I put on the archive last week. What it is if you change the background from Minkowski to Schwarzschild, the effects get larger when you're very close to the black hole by a factor of about 10. And then to conclude, measurable changes occur when GWs pass through matter. The effects are enhanced when the background is Schwarzschild and near the ISCO. The effects can be significant in these astrophysical cases. And the key point really that I want you to take away from this is that if you're in the long wavelength case, lambda is much bigger than the distance to the matter, all right, then one needs to think whether or not these effects are significant. And that's the key point to take home. And then perhaps then you should, if you're looking at such a case, then perhaps then you should go and look at those papers I put up at the beginning. Okay, thank you.
Thank you so much. Okay, so while I'm asking if Juan Carlos can already come to the stage, let's see him yet. See here, I'm looking at Ilya. Like the next speaker, Juan Carlos Rodriguez. Oh, online. Okay. So then, please, if we can start putting his screen on the projector. Are there any questions in the meantime? Like a quick question for Nigel? Yeah, Agnieszka. You beat me.
Thank you. Thank you. Impressive results. But I have a question actually about the third of your conclusions. Why do you say the effects are enhanced near the ISCO? I mean, near the ISCO, the accretion disk, for instance, is sometimes experiencing the magnetically arrested state. And here the magnetorotational turbulence may be somehow inefficient, which affects the viscosity. So I would guess that the effects are more stronger farther away from the ISCO in the accretion disk environment.
Skipped over to do with the background being Schwarzschild rather than Minkowski. If I'd had time, I mean, what that work shows is that if the shell is, if the matter is at a distance of a few m, I mean up to about 6 m from the gravitating source, then the effects get much larger. Okay, by a factor of 10. If the matter is somewhat further away, 10, 20 m from the source, then there's very little difference between the background being Minkowski or being Schwarzschild. So it was to do with that. It's nothing to do with the physics of the ISCO. Okay, and so that would change it in other ways, yes.
Okay, thank you. Okay, great. Let's thank Nigel again, and please feel free to ask some questions in the breaks.
Thank you.
Okay, then we'll now go to an online talk. Let's see.
Hello, everybody. My name is Juan Carlos Rodriguez Ramirez. I'm postdoctoral researcher at CBPF in Rio de Janeiro, Brazil. I am very delighted to present in this symposium our new analytical model for optical light curves as counterpart to binary black hole mergers. So in this talk, I will first introduce a brief motivation for the topic. Then I will discuss two particular scenarios for radiation flares driven by binary black hole mergers. And finally, I will summarize and conclude our results. Binary black hole mergers dominate the type of gravitational waves measured by the LIGO-Virgo GA experiment so far. Nevertheless, the astrophysical environments of such coalescences remain unknown. If measured, radiation signals accompanying these gravitational waves can provide valuable information to discover the astrophysical hosts. In addition, such multi-messenger associations are expected to find unprecedented astrophysical and cosmological applications. Here we focus on mergers in the central regions of active galactic nuclei, since, as proposed by previous works, AGNs found suitable conditions to form black hole pairs, and at the same time, AGNs' thin disk are gas-rich environments where significant radiation feedback can be produced. Indeed, optical flares observed, in particular AGN sources, have been investigated as potential counterparts to certain gravitational wave events by previous authors. So here we discuss under which conditions these AGN flares can be produced. Particularly, we quantify the emission of plasma ejections as expelled by binary black hole mergers. Since the proposed flares candidates are not yet confirmed as counterparts, here we do not aim to model such candidates. Instead, we investigate the emission features of potential disk eruptions driven by binary black hole mergers. So one way to produce disk eruptions is the propagation of Blandford Snagit jets launched by the remnants of a BBH merger. While propagating quasi-parallel to the disk, these jets inflate jet cocoons that eventually emerge and expand outside the disk. So in a recent work published earlier this year, we quantify the radiation of such emerging cocoon as a counterpart to the preceding gravitational wave. In this scenario, the jets are fed by Bondi-Hoyle-Littleton accretion, and the jet production is efficient provided the external medium is magnetized with a minimum plasma beta of around 10 according to previous GRMHD simulation performed by Cass et al. So under this assumption, in our work, we analytically quantify how much material the jet cocoon can collect. And then we calculate the flare produced when the cocoon expands outside the disk. In the spectral energy distribution on the right, we illustrated the type of solutions we are interested in, namely those where the flare outshine the host emission. The flare is plotted here with in blue curves, and the host emission is illustrated with the gray curves in this plot. In our formulation, we derive optical Lie curve for the electromagnetic counterpart. In this plot, for instance, we particularly illustrate the effect of the kick velocity and of the location of the merger on the Lie curve profile. We also analyze whether current and forthcoming optical instruments can observe these flares. More details can be found in our paper published earlier this year. It is not clear, however, how magnetized is the AGN disk at the location where the merger likely occurs, and therefore whether a jet can be produced by the remnant. So in a subsequent work, we do not assume jet production, but instead we consider supercritical winds launched by the remnant. Such winds are produced when the inflow rate onto the black hole is highly super-Eddington, which is typically the case for a binary black hole merger remnant within an AGN disk. We calculate the emission that results from the expelled material, and as it expands outside the disk. In our formulation, we identify two types of solutions according to whether the remnant lived towards the observer or in the opposite direction. The simultaneous inflow and outflow configuration assumed in this scenario is motivated by the interpretation of ultraluminous X-ray sources as supercritical accretors, and also by theoretical studies of Bondi-Hoyle-Littleton accretion with outflows. Under this model, the flares with delays of few weeks after the gravitational wave event are produced in AGNs with SMBH of the order of 10 to 6 solar masses. These relatively fast flares overcome the host emission at UV frequencies and can be comparable to it at optical bands. So we propose that binary black hole flares in these relatively small AGNs are suitable to targets for state-of-the-art facilities like the Rubin Observatory and the forthcoming Ultrasat for the case of UV flares. So in this plot, we illustrate the upper and the lower Lie curve solution in red and in blue curves, respectively, relative to the side where the remnant leaves the disk, as well as the effect of the kick velocity and of the Lie curve profile on the Lie curve profile. These effects on the Lie curve profile. So in our recent paper posted on the archive, we discuss up to which redshift the flares could be captured by different optical facilities. In this plot array on the right, we show the time delay of the flares as a function of the central SMBH, as a function of the mass of the central SMBH for different locations of the merger on the disk and for different kick velocities. The dependence of the time delay with the central SMBH appears quasi-linear. We obtain that for the case of central SMBH of 10 to the power of 8 solar masses and heavier, the delays are of year scales or larger. So the flares predicted by this model are not compatible with most of the candidates previously proposed by Graham et al., for instance. Instead, the The flares derived by this model suggest that AGNs with SMPH of the order of 10 to 6 solar masses are suitable targets to localize electromagnetic counterparts. In summary, we study AGNs, these air options, as driven by LIGO-Virgo-Kagra binary black hole mergers. And we found that we study particularly the scenarios of jet propagation as supercritical winds launched by the merger of a remnant within an AGN disk. We derive analytically time delay, time duration, and Likert profile of the eruptions as a function of the properties of the AGNs and as a function of the properties of the binary black hole merger. Such models are appropriate for localizing electromagnetic counterparts to BBH mergers in flaring AGNs. The predicted flares produce emissions comparable or exceeding that of the hosting AGNs, especially at UV bands and also on optical frequencies. We found that flares with a magnitude variation of 0.5 or larger can be better associated to gravitational waves in AGNs with SMPH of the order of 10 to 6 solar masses, as they have time lags of few weeks or months, according to the model described here. So thank you for your attention.
Thank you. So I'm just curious. So is Juan Carlos like online? Can he answer questions, or is it like purely video call? Online? Can you speak up if you're here? Or try to speak up? Say hi. Yeah. Okay. I see. See him yet? See among the participants? Like I know he's in a very different time zone, so it might be really challenging. Oh yeah. Oh, he's not allowed to speak. Oh, I'm so sorry about that. Yeah. Yeah, that can happen. I don't know. We see her here. We cannot unmute you, I think. I also don't see a video, so maybe it's something with the login. Oh, that's too bad. In that case, I encourage everyone to put a question online in the Slack. I don't think there's a special channel, but I think you can like message Carlos, like send a private message and look him up in the IAU Slack. Thank you so much. Michael, I think is here. Yeah. Nice. Please go ahead. We'll start with the next talk.
Okay. Oh, yeah. Thank you very much to the organizers for the opportunity. So I will present how we can potentially reveal extreme and intermediate mass ratio in spirals using quasi-periodic ultrafast outflows, or as we call them, QP outs. So not to confuse with QPO or QPs. And so this is the basic picture. So binaries where a smaller black hole orbits a supermassive one in the centers of galaxies are considered as precursors of low-frequency gravitational wave events. And of course, it is of high interest to search for such binaries using electromagnetic counterparts. And in most of the previous talks, people presented ideas or models for the emission. So instead, I will try to propose a new way where one can search for such binaries using quasi-periodicity in X-ray absorption. And this has been actually motivated by an actual source or associated first with optical flare assassin 20QC in a relatively nearby source, which was discovered on December 2020. And actually, subsequent spectroscopy and broadband photometry revealed the black hole mass of about 10 to 7, 10 to 8 solar masses, like the primary black hole mass. And so this was actually the light curve. The blue points reveal the optical light curve, and this can be interpreted as a relatively standard tidal disruption event with some kind of a plateau here. And subsequent monitoring revealed X-ray emission. So previously, the galactic nucleus was rather low luminosity, AGN, not even detected in X-rays. But about 52 days after the first assassin detections, we've detected X-rays, which has been also done for other TDEs. So this is basically the X-ray emission here. So then these are just upper limits, and it went up quite significantly for about 100 days. And afterwards, the source decreased in X-ray luminosity by about 2 orders of magnitude. And NICER performed high cadence monitoring started on February 13, 2021. And also XMM Newton took several X-ray spectra. And so this looks like a standard tidal disruption event with subsequent X-ray emission due to the formation of compact disk. However, what has been interesting for this source when one analyzes the X-ray spectrum is that there is a thermal emission, and so here is the normalized X-ray spectrum, but one can detect there absorption, which can be interpreted which can be associated by ultrafast outflow of about 1/3 of light speed. And one can calculate a ratio of the flux between this outflow band and the inflow band at lower energies. So this is what we call ODR, or outflow deficit ratio parameter. And actually this ODR, this ratio exhibits a significant periodicity of about 8.5 days, where the lower ODR indicates an enhanced ultrafast outflow and a higher lower one. So there is this recurrent UFO or ultrafast outflow, and one can perform tests, so of course calculate the Lomskarger periodogram and the significance of the periodicity and the recurrence. And actually it's pretty significant that about 4 sigma level. And so this is how basically we detected this quasi-periodic ultrafast outflow, or QP out. One can also detect it using other methods like the phase dispersion minimization or weighted wavelet Z transform. So there is always this periodicity of about 8.5 days. And what is actually interesting for this source that normally one expects, like due to shocks or breakout emission, as was mentioned in the first talk, that there is actually, there should be periodicity normally in such a system, or maybe if there is a binary in a like this band at lower energies associated with accretion or inflow, but that's actually consistent with stochastic red noise behavior. So it's basically just this band at higher energies where we see this absorption that shows this periodicity, and then also the ratio mainly shows the periodicity. So it's clearly this ultrafast outflow that is being enhanced, and every 8.5 days. And one can also trace some the variability in properties of this outflow. So when there is a minimum of this outflow deficit ratio, so stronger ultrafast outflow. So as we would expect, there is larger column density and also larger ionization parameter. But interestingly, the outflow velocity is not changing significantly. So it's about 0.33 or 35 of the speed of light. So when we went through different scenarios, like in a disk precession. So this would mostly lead to changes in continuum flux. Clump event, we would expect rather stochastic variability. X-ray reflection should be associated with the harder power law component, which is not detected in this source. So it's quite a soft source. Magnetically arrested disk would, from previous studies of GRMHD simulations, one would expect higher outflow velocities. For QPs that we discussed, like quasi-periodic eruption sources, they are associated mostly with quite significant continuum variability. So this is a different kind of variability. And repeating partial TDs, they have continuum variability at longer periods. And radiation pressure-driven outflows. So since the source was previously rather low luminous, normally we would expect this radiation pressure instability to not operate in such a source. So in the end, we focused on ultra-fast outflow that is driven by an orbiting perturber. And we performed also independently before this detection several 2D and 3D GRMHD simulations where actually such behavior when a perturber is crossing an accretion flow, so this is in the paper by Sukova 2021, one can basically detect both quasi-periodic variability in accretion and also outflow. So in this outflow funnel, so we were basically tracking the Lorentz factor and also outflow rate. And so we used our simulations, so in a collaboration with the colleagues from MIT, to constrain the nature of the perturber, or how big perturber or massive perturber one requires to reproduce such ultra-fast outflow. And for this, we use the observed ratio between outflow and inflow rate as a function of time. And we compare it with the simulated outflow and inflow rate. And the basic conclusion was that we need the perturber that has influence radius of the order of gravitational radius or of the primary black hole, or more specifically about 3 gravitational radii. So then given the uncertainty on the primary black hole mass, this puts a lower limit on this perturber mass, so which puts it into rather high mass stellar black hole or intermediate mass black hole range. And the upper limit we got from the statistical condition that basically, since in this source we observed a TD or TD-like event traced by the optical emission. So statistically, since there should be some binary system, so the merger timescale should be longer or comparable to about 10,000 years for TD to likely happen in such a system, because otherwise the merger timescale would be too short and we wouldn't see TD in such a binary system. So this puts an upper limit on the perturber mass of about 10,000 solar masses. So then this is the scenario that I sketched here. So there are 2 possibilities. So either TD is not really related to the binary system, so there was just a random star that got disrupted. Or potentially, since there are several dynamical models of infalling stellar clusters, this could be like the remnant core of such a cluster. And basically the IMBH brought these stars that got disrupted. So these are maybe 2 possibilities, of course, hypothetical ones, but that we discuss in this paper. And so the main pros of this perturber-induced outflow with the perturber in the IMBH range is that it can capture quasi-periodic ultra-fast outflow. So dense enough outflow that can basically block the light, the emission of the formed accretion disk. Then from the simulations, if the perturber is at about 100 gravitational radii, which corresponds to the orbital period of this 8.5 days, so when we are looking close to the rotation axis of the system, so then there is no significant periodicity in the inflow as is observed for the system, but still there is significant periodicity in the ultra-fast outflow. And for the primary black hole mass in the range of 10 to 7, 10 to 8 solar masses, since we require to produce such dense enough outflow, so from this influence radius condition that it should be larger than about 1 gravitational radius, or ideally 3 gravitational radii. So for this primary black hole mass, black hole perturbers are more likely. Tidal disruption of a solar mass star is basically here. So for so this is basically the condition of this is derived from the condition on the tidal disruption. So normally we wouldn't expect such perturbers of solar nature, of stellar nature, to be so large for this primary black hole mass. But of course, if there are sources with a lower mass, with such periodicity of, as was observed here, of about 8 days, then also stellar perturbers could then be consistent with this condition of about 1 gravitational radius. So this is another reason why we prefer this perturber to be an IMB, intermediate mass black hole for this particular source. So in conclusion, so some takeaway messages. So also in the context of extreme mass ratio and intermediate mass ratio in spiral. So currently we know generally we know very few cases of about concerning intermediate mass black hole, and they are supermassive black hole, intermediate mass black hole binaries are still quite hypothetical, but we may see such indirect signatures as I presented here. So these quasi-periodic ultrafast outflows, as seen in this source, are a new type of transient with a significant perturbation in the outflow rate. And this may be another way, observational way, to look for such binary systems. And in this particular case, this is a source with a period of 8.5 days, which points towards IMBH perturber at about 100 gravitational radii. And the results were published in this paper led by DJ Dheeraj Pasham in Science Advances. So thank you very much, and I'm looking forward to your questions. Thank you.
Thank you so much. So while we're going to go to the question, Agnieszka, if you haven't checked your mic, okay, perfect. Are there any, I see a question there in the back of this.
So this perturber will be moving highly supersonically through the gas, right? So would you not expect to shock heat this plasma and produce more than just an outflow that gets in the way?
Yeah, we did some estimates, and yeah, for this particular source, so there is shock emission, but the maximum X-ray luminosity would be of the order of 10 to 40 ergs per second. But here, actually, as I was showing at the beginning, the X-ray luminosity was of the order of 10 to 43 ergs per second, right? So it was actually above. So then, if there is any shock emission, so when we were calculating it, it's probably below this continuum emission. So it's for this source, it's just difficult or not easy to detect it. But for maybe there can be configuration, of course, depending on accretion rate, where also both outflow or absorption periodicity and also like emission periodicity can be observed like in the future.
See a question in the back.
Hi, thanks for the nice talk. Just want to know, like, what's the uncertainty on your periodicity? And have you calculated like any confidence level on the periodicity that you have, like 8.5 days?
Yeah, it's here. So this is basically 4 sigma or above 4 sigma. So this is presented in actually there were Monte Carlo simulations that we performed, and tested. So this is presented in the paper by Pasha et al. So because we observe about 12 cycles, so this is not just 2-3 cycles. So indeed, it appears to be, or even by eye almost, but also from the Lomskager periodogram, it is significant. But unfortunately, then as the X-ray level dropped because of the gas was consumed from as presumably TDE event, then it has been challenging to detect, to further monitor the source because the X-rays went down. But of course, presumably the binary is still there. Yeah.
Any other questions? Okay, while the next speakers come up, I actually have one question that I wanted to ask, which is, I thought for this like cluster accretion scenario where like the clusters falls in and so the star is associated with a black hole. Yeah, I think we have to go to the other slides, but it's okay. I was just wondering, is there like a time scale that's associated with that? Like I thought that happens mostly at the beginning of the black hole, like when it's still a young like galaxy supermassive black, like AGN.
You mean this kind of like
Accretion.
global cluster infall, or yeah, I think there is. So we haven't studied this ourselves, but there are these papers actually which go all the way to Spitzer and so on. But recently, I think Fragione studied this and calculated the rates as a function of redshift. So you can check that paper for more details. Yeah.
Thank you so much.
Thank you. Thank you very much.
And we can go to the last great talk of today on AGN topics by Agnieszka.
Yeah.
So.
Good afternoon, everybody, and thank you very much for staying so long until the last talk of the session. And I hope my presentation will be launched in a couple seconds. Oh, it's here. Okay, let me go to the first slide just to introduce myself for those of you who don't know me. My name is Agnieszka Janiuk, and I come from Warsaw, Poland, Center for Theoretical Physics of the Academy of Science, and I'm leader of the relativistic astrophysics group there. And today I want to report about the project done in collaboration with my former postdoc, Fatema Hossein Nouri, who's been working in CFT for the last 3 years, but recently she moved to the University of Milano. And the topic of the viscous torque in turbulent magnetized accretion disks to account for the effects of accretion disk environment in the extreme mass ratio in spirals. So this is just a definition from Wikipedia. What are these? IMRIS acronym. So they are relatively light objects orbiting around much heavier ones. Presumably they are the two black holes of the very unequal mass ratio. So as we heard today during the discussion session, maybe the people from Gaia Observatory are mostly interested in those. If you imagine having a stellar mass black holes orbiting the supermassive black hole around the center of our galaxy, this characteristic strains lies in the frequency band of the future space-based detectors. And such a detector planet is currently now approved by ESA and is going to be launched probably in the 10 years from now or so, and will orbit the Earth in the form of the set of 3 detectors interconnected with each other with lasers located 2.5 million kilometers on the arms of the equilateral triangle. And for me, the interesting case is not this extreme mass ratio in spiral, which I defined in the first slide, but now I'm interested in the mergers in gas-rich environment that are actually a little bit less extreme, but still you can have the mass ratio about 10 to minus 3 between the two merging black holes that are relatively close to each other already in the final parsec distance or closer. And they are supposed to account for observed behavior of several interesting sources. The active galaxies named here, GSIN 069, NGC 5548, and so on. Their characteristic observations showing signatures of a secondary black hole orbiting the primary one are found in electromagnetic domain and inspire such studies as ours. And all we know that the supermassive black hole in the AGN center is surrounded by an accretion disk. So the question is whether this accretion disk would have any measurable effect on the emitted gravitational wave signal if we are lucky enough to detect such a signal with future interferometers. So a number of works have been proposed in the last decade or more on this topic. Most of these works relied on a simple description of the accretion process that is based on the formalism proposed by Shakura and Sunyaev 50 years ago. And it is so-called alpha prescription for the viscosity in the accretion disk. The viscosity is driving parameter here, of course, because it is responsible for the viscous torque and transport of the angular momentum within the disk. And this angular momentum will presumably affect the binary parameters if we have the binary objects spiraling around each other within such an environment. But the alpha viscosity prescription is known to be quite simplified because in this model, the viscosity does not depend neither on time, nor on the location within the accretion disk. It is assumed to be constant and have the value between 0.01 to 0.1 or more, depending on the authors. People, of course, estimate more precisely the value of alpha in numerical simulations. And this is what we do in our work as well, because we study the magnetic field evolution to provide the physical mechanism for the angular momentum transport via the MRI, famous bulbous and Hawley mechanism that is responsible to drive the angular momentum transport and is actually equivalent to this alpha viscosity. So what is our tool? It is the general relativistic MHD simulations. This is the keyword frequently used here in this symposium. So it's also good to remind you what the keyword stands for. It stands for solving the basic equations of physics, the continuity equation and conservation of mass energy, where the stress energy tensor is expressed in this form, so that it can in general include the mass and electromagnetic part. And basically these equations of the continuity and energy momentum are supplemented with the Maxwell's equations. So we are all owing the tribute to these three Western European white men that gave foundations to our work, and still we are working within the paradigm that was established in their seminal works. We are using numerical methods nowadays. So the equations which are not possible to be solved analytically, they are discretized on numerical grid. And standard methods, finite volume methods mostly are used to solve these equations on the three-dimensional grid. Actually, there is a fourth dimension as well, because these are the space-time components of the tensor, and this is what we are working with. I have my code for that, but of course it is based on the very well-known HARM, high accuracy relativistic magnetohydrodynamics scheme proposed in the late 90s and beginning of 2000, and used by various groups in the community. So not to go into many details of the code because it has a lot of other features which will not be used here in this project. This project was based on the initial configuration evolved from the state of the geometrically thin disk. We have a thin disk prescribed in the initial condition. This is the equation describing the distribution of the density in the equatorial plane. Here are some parameters like the polytropic constant, the temperature, dimensionless temperature in this disk, and some functions described in the paper and in the references therein. We use the polytropic equation of state for the disk with the index 4/3 here, and we provide the magnetic field configuration also initially accounting for the poloidal magnetic field, described in such a way that this parameter here scales the configuration which could be either more inclined with respect to the equator or less inclined. This inclination angle depends on the parameter m, which is a number between 0 and 1. We use here 0, 1 and 0, 5 for the test models. The models are also parameterized with the strength of this magnetic field, which is scaling with the ratio between gas and magnetic pressure in the maximum point of the grid. And we parameterize models with the black hole spin value, which is a Kerr black hole. So let me show a sample simulation movie. Here you see the 2D simulation run. It is running up to 60,000 geometric time units. And you see how the thin disk initial configuration evolved with time. There is some kind of a small structure developing here in the center, which is kind of a thickish torus. It is actually equivalent to the ADAF, innermost advectively dominated accretion flow. And it is geometrically thicker than initially. And here, magnetorotational turbulence has developed already, and you see turbulent flow in this equatorial plane. Let me show the end configurations of density and magnetic field distribution for a sample of models which we studied. Here you see also another interesting case, the magnetically arrested flow format here. So you see the barrier pushing away the disk from the black hole horizon. This model is represented here with the blue line, and this quantity here on the y-axis is called the madness parameter, which describes the effect of magnetically arrested state in the disk. If it is large with respect to the mass accretion rate, then we call it arrested disk. So the disk cannot actually accrete effectively, and accretion rate is temporarily dropping to 0. But yeah, this is what we studied in the simulation, but our main goal was, of course, to describe the viscous torque, quantify this viscous torque, and compare it to the gravitational wave torque, and to compute the numbers we need to evaluate this alpha viscosity parameter here numerically. So as you see, it depends on time, it depends on the location. Here is actually the quantity being the volume averaged alpha, but we can compute any kind of number in the grid as well. And here our alpha is composed of two components, the Reynolds and Maxwell stress components. The Reynolds one is described here with velocities, and the Maxwell one with magnetic force vectors. And as you can see, the Maxwell one is dominant for any model which we studied, and the effective alpha number is reaching 0.3. It is important for our results. So this is the results for the torque. Yeah, the gravitational waves torque is computed with such a formula where Q is the mass ratio and MP is the primary mass. And our viscous torque is computed with such a formula where the viscosity quantified with alpha, effective alpha value, speed of sound is entering here with some kind of numbers, relativistic correction and so on. So as you can see, the ratio between viscous and gravitational wave torque can be as large as 10 to minus 2. Yeah, at some distance from the black hole expressed here in gravitational radii. This is the ratio for our 3 models. The 4th one is skipped here, the one I mentioned, which is the most magnetically arrested one. But here are the 3 other models we studied. And of course, these parameters are very important here. Most important is the mass ratio, Q. The smaller it is, the larger the effect, of course. Yeah, but here is some kind of conservative value, which could be relevant to the sources which we are interested in. And this is the final result. The effect, which can be probably measurable, is the effect of dephasing of gravitational wave signal due to the accretion disk effect. And this dephasing computed with such a formula where R dot is the change of the separation of the binary black holes merging, and here this L dot is the flux of angular momentum brought by the viscous torque. Here you have alpha, here you have speed of sound and local density. And here the quadruple formula provides the gravitational wave effect. So the resulting number estimated in our work is this, about 10 radians. 10 radians in 10 to 5 orbits. Yeah, so this is the number which we derived. These are my conclusions. So this magnetic field triggers magneto-rotational instability and turns the accretion disk into the mat state. From the numerical simulations of magnetically arrested disks, we can measure the effective alpha parameter. The density weighted volume average varies around 0.1, 0.25 roughly. And we applied our results to measure the viscous torque from accretion disk. It can reach a few percent of the gravitational wave torque, around 100 gravitational radii from the black hole, from the primary. And this is given for the mass ratio of the extreme mass ratio in spiral 10 to minus 3. And the extra torque from environment appears as a phase shift in gravitational wave signal quantified in our work. So I would like to thank the computational resources provided by the PL Grid and to the postdoc Fatima, who is the first author of this paper published this year, just very recently. And finally, I want to advertise the conference which we are organizing in the coming month. Michał Zajacek is one of the SOC members as well. So the conference will be addressed to CL-AGN, Changing Look AGN. If you are happening to have some kind of motivation to come to Warsaw in September, we advertise our event, in addition to other very famous events such as Taylor Swift's concert last weekend gathered 2 million people coming to our city. Thank you.
Thank you so much. I was curious when the first Taylor Swift reference was going to be made. Are there any questions? I'm sure there's good questions before we end the session. I see one.
So your simulations were 2D, is that correct?
No, the models I shown here were 2D, but we performed extra 3D simulations to verify the results as well. I didn't show the plots here. They were qualitatively a little bit quantitatively different alpha, but qualitatively similar with respect to the 2D. The axis symmetry was preserved, yeah.
Because it's quite hard to measure alpha in a 2D because your turbulence dies because of no dynamo theorem.
Yes, that's true. So our simulation were long enough to establish the quasi-stable accretion flow, but of course, the longer simulation run, the stronger the effect of anti-dynamo. You are correct. So that's why we ran this 3D model as an extra work to test.
Okay, thank you.
Yes.
I'm just seeing if there's any other hands up. I had one quick question. You mentioned that the smaller black hole is like not modeled in the hydro simulation. So can that be an issue, or is it just?
Yeah,
like,
that can be a big issue, of course. Yeah, in our simulation, this is the greatest simplification, of course. So if we account for accretion onto this small black hole and extra force effect within the simulation, we would need to add one more equation to the code, and yeah, to do it. Mm-hmm.
Thanks.
Yeah.
Okay, with that, let's thank Niska for a great talk. And then we reached the end of the session. I just want to remind that tomorrow at 10 a.m. there's a great gravitational wave posters that you can view in the big hall if you haven't done so. So please pass along so you can also support many of our early career scientists that have posters here. And let's just thank the AV also for all the work today and their great job running around. So thank you everyone and have a great day and lots of fun discussions.